I'm Nimi Nasragasa. I'm a faculty in the Department of Skill and Environmental Engineering, and I am the instructor for senior design. So I would like to welcome you all to the 39th Projects Day. I heard it was 38, but after 30, it doesn't really matter with the this year we have completed 6 civil engineering projects and 1 environmental science project. So the first hour, we will listen to 3 civil engineering projects, then we'll take a 15-minute break, and then listen to the next 3 projects starting at 2 o'clock. So before we get started, I'd like to invite our department chair, Dr. West Lauer, to come and recognize your paper engagement.
All right, well, so many of you know that the Civil Engineering Department gives an award to what the faculty recognize as the top civil engineering student of the year. This year, it was a clear choice. The faculty are very proud to give this award to Carl Christopherson. So if you don't know Carl, and I want to get a photo here, but yeah, there you go. So Carl, if you don't know, there are a lot of reasons for this award. First of all, Carl has one of the highest GPAs I can remember in the major. It's really impressive how well you've done in all of your classes, Carl. In addition to that, Carl did a lot of other things. So Carl did an REU in Southern Florida, University of South Florida, in climate resilience. He worked at BHC Consultants as an intern. He tutored in the Math Center, and he worked at Camp CASM as supporting youth. So, all of that is the kind of thing that we in the department really value. So we really appreciate all the time and effort you put into it. And as you'll see in their presentation, he and the rest of his team did a lot of really amazing work on their project. So join me once again in thank you.
So we start with our first project. The project is sponsored by Covington Water District. This is the 4th project that they are sponsoring. So thank you for their continued support. And with that, I'd like to invite the speaker.
All right, welcome everyone. There's a lot more people in here than there were when we practiced on Wednesday, so very exciting. We're team CE 26.1. I'm Carl. With me, I have Matthew, Anya, and Lexi. And this year we worked with Covington Water District on the Sugarloaf Water System Improvements Project. To give you a brief outline of what we'll be talking about today, we'll start with our project background. We'll go through our scope of work. We will talk about our water model. We'll give you some details on our input and our output for that. And we'll give you an overview of the alternatives that we considered. And then we'll go through our evaluation process and we'll talk about the alternative that we are recommending. And a huge thank you to everyone that was involved in this project this whole year. We couldn't have done it without you all. At the top, we have our liaisons from the Water District, Amber, Joseph, Steve, and Tom. Our project coordinator is Dr. G, and our project manager is Dr. Rossi. And then our team is across the bottom line.
All right, now going into where our project site is located. It's approximately 30 miles outside of Seattle in Ravensdale, Washington, highlighted in this yellow square here. So zooming into that, we have a project site. The water system serves 2 communities, one being the Sugarloaf Estates community, which we'll be focusing on today, and then also Sugarloaf Mountain community to the north. These 2 neighborhoods get their water source from here in the circle, which is the well site.
The well site consists of 2 wells and a well house, which chlorinates the water and sends off to 2 water storage tanks. The estates tank, which is a small 18,000 gallon tank that sits at the elevation of the neighborhood it serves, requiring booster pumps to maintain adequate water pressure, and tank 1, which is a 100,000 gallon tank that serves the Mountain Estates neighborhood. Due to increase in water demand, the district plans on building a new 250,000 gallon tank called Tank 2. Along with that, they'll be decommissioning the estates tank. It was our goal to determine the most optimal connection between Tank 2 and the estates neighborhood.
In order to determine the most optimal distribution method, we have to model our system. Water modeling software such as WaterGems, InfoWater, and MyPlus all run on EPNet hydraulic engine, have similar capabilities and are expensive. Since these options exceed our project budget, we looked into EPNet and WNTR Python libraries. They use these same calculations and are both free. On the left, we have an EPNet model sample. As a simple visual, is hand-drawn and requires manual entry, which is difficult for a network with over 500 pipes and nodes. On the right, compared to the right, is our WNTR interactive model that has geographic context and uses Excel input sheet that's easy to modify.
So what is WNTR, the Water Network Tool for Resilience? It's a Python package that allows custom scripts created by the US EPA that allows custom script to access EPNet's hydraulic engine or its ability to do hydraulic calculations. What that meant for our project is that it allowed our custom Python script that we developed with the help of our faculty advisor to take a number of these inputs and turn it into a water model. It created results in the form of Excel files, charts, and a time series animated map that Anya showed in the last slide. We'll go more into detail on all of these inputs and outputs in the coming slides. The simulated water network required certain flow values such as peak flow, peak average daily flow, and minimum daily flow. To define these values, we requested 10 years worth of flow meter data from the district. We then created a Python code to analyze the data, produce the values that we need. To ensure they were correct, we hand calculated a small sample size and ran the code to compare. We also generated charts and graphs to visualize it. As you can see here, this is a chart of the peak flow for all 10 years. The maximum for that 10-year interval was 70 gallons per minute. To go into some more detail on the input data that we prepared for our model, we started with the GIS data provided to us by the Water District, and we converted it into a form usable by our script. The first thing we did is we placed nodes that you can see in this map on the right here at every change in direction, change in material, change in diameter, and all of the service meters within the system. Next, we connected them all with a system of pipes. Coordinates and elevations were calculated for everything based on a USGS digital elevation model, LiDAR. Using ArcGIS Pro, you can see a summary of the system in the bottom left-hand corner here. In total, there are 280 nodes, 291 pipes, 99 service meters, and almost 26,000 total feet of pipe. Next, a pump curve was approximated based on the total dynamic head required to lift water from its depth in the aquifer all the way to the top of that new tank at reasonable flow values. And then all of that data was packaged into individual Excel files for each of the individual trials that we ran. For each of those trials, our model produced a number of results. The first, that animated map that you can see an example of on the right side of your screen here. Next, we have charts displaying water age and pump on-off cycles over the length of the simulation. And then we have those Excel files displaying values over time for parameters such as major head loss, water age, pressure, flow, velocity, and tank level. One important capability of our animated model is that we can access localized information at pipes and nodes within the system. This was incredibly helpful for our iteration process. Now, as I run this model, pick a node. I have one highlighted with that red arrow there. And as I run it, you'll watch as the colors change, as the pressures within the system lower, as water is distributed from the tank, the level lowers and the hydraulic grade line within the system lowers as well. At a certain point, the tank level will get low enough, the pump will kick back on, the tank will refill, and pressures will be restored to what they were originally, and the colors will go back to what they were at the start.
All right, now going into the three alternatives our team analyzed using WNTR, we have our first alternative here, which utilizes the existing water main within the system. So water will be supplied to Tank 2 and also the SUGARLOAF Estates community, split in flow and until the tank is at capacity. Once tank is at capacity, it can switch direction in the pipe, bypass the well house and into the SUGARLOAF Estates community to serve them. Alternative 2 abandons that southern pipe there, so all the water from the well house will be supplied to Tank 2. Then to serve the community, we are proposing a newly constructed pipeline here highlighted in the red. And that'll be connected at the northeast end of the community. Alternative 3 is a combination of the previous two alternatives. So in the same way of alternative 1, it'll split flow at the well house, one to fill Tank 2 and one to the SUGARLOAF Estates community. Then once at capacity, it can utilize bidirectional flow within the existing water main, as well as utilize that newly constructed pipeline that we are proposing to have two connections within the water network, and this will create a loop system for the district. For alternatives 2 and 3, I noted that we are looking into a newly constructed pipeline. We aligned our pipeline in accordance to the existing easement that the water district had provided to us, which goes through 4 different parcels of land and totals to about 1,400 feet of pipe. With this in our analysis, we analyzed 4 different pipe diameters, being 6-inch, 8-inch, 12-inch, and 16-inch.
Here's our fully graded decision matrix. We have 6 criteria: hydraulic performance, cost, maintenance, constructability, permitting, and future considerations. We met with our sponsors and discussed their preferences, and we came up with the grades that you see here.
For hydraulic performance, we assessed 3 factors: pressure within 30 to 80 psi, velocity less than 8 feet per second, and water age with a typical value of no more than 3 days. This is to avoid chlorine decay and stagnation. Water age is how long water has been sitting in the pipe since it left its source. On the right is our initial metric for hydraulic performance. To find the highest pressure from the system, we use the minimum daily demand. To find the lowest pressure from the system and the maximum amount of head loss and velocity, we use the peak hourly demand. And to evaluate water age, we use the average daily demand and simulate it in an extended period of time.
Based on the results of our trials for all of our alternatives for these 3 testing conditions, our first finding was that for high pressure scenarios, all of our alternatives performed similarly. So those were left out of our final analysis. Our next finding was that maximum water velocity was well below that mandated 8 feet per second for all of our alternatives. So that was also left out of our final analysis. Next, we concluded that low pressure scenarios, total system head loss was an effective representative measurement because head loss is the energy that water loses as it travels through pipes and around bends within the system. Water stores energy in the form of pressure, so the higher head loss the system has, the lower pressure we'll see within the system and at connections when you turn your faucet on in your home. So in the end, we ended up with 2 criteria for our final analysis for hydraulic performance: total system head loss, and a metric related to water age, related to flexibility and operation for the system's operators to ensure adequate turnover in the tank and maintain average water age that is reasonable. Now to go more into depth into our grading for some of our more important parameters, we'll start with hydraulic performance. At the top, you can see small visuals representing the 3 alternatives to remind you what each of them are. And then in the table, you can see our final grades for total head loss and for water age performance. The results of each alternative were graded on a scale of 1 to 5, 1 being the worst, 5 being the best, all compared to each other with slight adjustments per scale.
Now getting into the money aspect of the project, our team created a cost analysis of each alternative and their respective pipe diameters for alternatives 2 and 3. So for alternative 1, we found that it's approximately $74,000 according to existing bid tabs that we were provided to by the district to create our engineer's estimate. So it got graded a 5 since it's our most cost-effective alternative. This is due to the rerouting and valves that we need to do for ensuring bidirectional flow within the existing water. Alternative 2 gets a lot more expensive because it deals with laying down the new pipeline. So with that comes vegetation clearing, connecting to existing water main, and abandoning pipe, as well as a lot more things. Alternative 3 gets slightly more expensive because it's a combination of the previous 2 alternatives. So rerouting, installing valves for bidirectional flow, as well as constructing that newly proposed pipeline that we're proposing. With that, we found that our least cost-effective solution is alternative 3 with a pipe diameter of 16 inches, and that got approximated to about $1 million, so it got rated the low score of a 1.
This is our fully graded decision matrix. Since we already covered hydraulic performance and cost, we'll be continuing with maintenance. For alternative 1, we scored it a 1. This is because it is a branch system. Alternative 2 is also a branch system. However, it has new piping, so it's graded a 3. And alternative 3 is going to be a loop system. This means that part of it can be taken offline for maintenance while the rest remains operational. Therefore, we grade it a 5. For constructability, alternative 1 was graded a 5. This is because there's very low construction. Alternatives 2 and 3 were graded lower based on their pipe diameter. For permitting, since alternative 1 has limited construction, it requires limited permitting, so it was graded a 5. Alternatives 2 and 3 both required a new pipeline to be installed, which requires numerous permits such as clearing and grading and right-of-way, therefore it is scored a 1. For future considerations, alternative 1 was scored a 1 because it's not very adaptable. Same with alternative 2. And alternative 3 is a loop system, meaning it has more connections and will have large diameters, and it's better.
On the bottom, we have our final grading, and we can see that alternative 3 is our most effective alternative with a max grading of a 3.5. So our preferred alternative alternative 3 with an 8-inch pipe diameter.
After recommending our preferred alternative to our sponsors, our team proceeded to complete a 30% design of the new pipeline, which includes profile views of that new pipeline, as well as details around the well house, and also decommissioning plan for the Sugarloaf Estates tank site. Questions? Okay.
Yeah, I have a presentation. Actually, brilliant job on the analysis presentation. One of your slides had the different parameters that you did for scoring. I was wondering if each of those parameters were equally weighted, or should there be more of one parameter, was more should be weighted more than the other?
Yeah, to read your question, so make sure I'm understanding correctly, it's how we weighted each criteria and like why we didn't equate them equal all to each other. Mm-hmm. So really the main aspect of it is with this modeling, we want to make sure that the customers always have adequate pressure and that it works well. And also with like the cost of things, that's also a big driver in the decision-making process. Constructability and like permitting and future considerations, they are big parts of the evaluation. However, with discussing with our sponsor, making sure that they have the best hydraulic performance is definitely.
So like with head, I just want to make sure, I'm an engineer, so that's why I'm asking. So would the head loss weigh more in your scenario than versus future consider? Oh,
These are the weights.
Those are the weights. Oh.
It doesn't say weights on this.
Okay,
There's too many
perfect.
things to say in the table,
Okay.
so I got left out.
Thank you.
Sorry, listening to this.
Congratulations again on your modeling and on your presentation. Very clear, great presentation. I'm curious about your fire flows. Did you consider fire flow at all? And the fire flow demand, how would that affect your pipe diameters and your analysis?
Thank you for the question. So the question is related to fire flow, and we considered it in our analysis. So luckily for us, we didn't have to consider fire flow. Typically, fire flow is one of the most important parts of modeling, is ensuring we're meeting adequate pressures under fire flow. But because the system runs on wells, and the wells only have a certain water right that they're already almost meeting entirely what they're allowed to pull out of the ground, so they're not able to provide fire flow. So all the houses have their own sprinkler systems to handle that.
Any other questions? Thank you, Dean.
That's fun.
Yeah. How do you start about? Yeah. And yeah, it's has no wants from us. I just like I think I saw that first time too. I saw it. And they so much
People, yeah.
Yes.
Did you know?
I did too.
He forgot that.
Yes, that's true.
Yeah.
Hi everyone, we're on TMC 2644. I'm Daniel, and here are my teammates, Chris, Lisa, Jennifer, and Eric. And this is our project, which is a seismic evaluation of the TOLT powerhouse located in Woodland, Washington with Seattle City Lights. So a little overview on our team structure. The project is sponsored by Seattle City Lights, which is represented on the top by Peter, Houston, and Robert. In the middle is our faculty advisor, Dr. Smith, and our design coordinator, Dr. Kim. And down below is us, the engineer. Now, Luis is going to talk about the background of the site.
Our powerhouse is 35 miles from the city of Seattle, and it's upstream of Carnation. Here's a bird's eye view of the surrounding area. We have a reservoir and a regulating basin. Our powerhouse is right outside that regulating basin. This is a north side image of the powerhouse. The powerhouse was finished construction in 1995 and started operating that same year. Now Luis is going to talk to you guys about our building description. I'm sorry. Our powerhouse is located in the high seismic zone because there's 3 sources of seismic waves. There's the cascading subduction zone, there's deep and crustal earthquakes, and now Luis is going to talk to you guys about the building structure.
So this is our building plan view. As you can see, in blue is our main building, which has 1 story. In red is our office building, which has 2 stories. The entire building is made of precast concrete panels, which are yellow. These are our shear walls, which is a main structural component that's going to be resistant to lateral forces, such as seismic forces. In the event of an earthquake, these walls are going to take the north-south component of the earthquake, and these are going to take the east-west component of the earthquake. These are our building elevations. So you can see, picture on the left shows our main building is about 37 feet tall, and our office building is about 23 feet tall. In the picture on the right, you can see in blue is one of our precast concrete panels. These are about 8 feet wide. These have these steel plate connections that are embedded into the panel, and coming out of it is number 5 bars that are then embedded into the next panel, and then they're welded. And that is how the panel to panel connection looks like. Onto more structural components, you can see in the picture on the left, we have a truss with yellow. This is an AOH 28 steel joist. We're gonna go from north to south. There's space 4 feet apart. And then picture on the right is just a more close-up picture of the truss. And then on top, you can see the steel deck, which is 1.5 inch corrugated steel deck. And you can also see the concrete walls from the inside. Now Daniel's going to talk about the problem statement.
So the powerhouse is a key facility of Seattle water drinking system, And although the powerhouse doesn't generate power for the city of Seattle itself, its primary importance is supporting continuous water delivery and treatment, which makes maintaining its functionality critical. However, the powerhouse was built before current seismic code provisions, meaning its ability to resist earthquakes is uncertain. And because the powerhouse is located in a region influenced by earthquakes, a major seismic event could happen and cause significant structural damages and disrupt power generation. And since it's a key facility, Seattle City Lights needs to ensure that it remains safe and operational even after an earthquake. So for that reason, our team has performed an assessment following ENSC 41-23 and the Seattle existing building code for retrofit. Now, Eric is going to talk about the risk category of the building.
Before we can start our assessment of the building, we first need to determine the performance objective of the building during an earthquake. In order to do this, we first need to determine the risk category of the building. Risk category, as defined by ASCE 7-22, goes on a scale of 1 to 4, where 1 being low risk to human life and 4 being an essential building like a hospital. As mentioned earlier by Daniel, because this is a key facility, we can then classify this as a risk category for a building. From this, we can then use ASCE 41-22 to determine the performance objectives based on these two hazard levels using new building design standards. We'll be using new building design standards instead of existing building design standards as requested by Seattle City Light. So for a BSCE 1N or a rare seismic event, it will require immediate occupancy performance. Immediate occupancy performance means that during an earthquake, the building sustains minimal damage, and after an earthquake, people can immediately occupy the building, making it operational again. Meanwhile, for a BSCE 2N or a very rare seismic event, it will require a light safety performance. Light safety performance means that during an earthquake, the building sustains some damage, but doesn't fully collapse. Additionally, after an earthquake, people can safely leave the building in a safe manner. Once we know our performance objectives, we can then use the AAC hazard tool to generate the hazard spectra at the location of our project. As shown here with the BSCE 2N spectrum. On the x-axis of the spectrum is the period, or the time it takes for the building to complete one full oscillation cycle back to its original position in seconds. And on the y-axis is the spectral acceleration, which is just the dip in acceleration from the earthquake onto the building, which is just a multiplier of g, which is gravity. So how we're going to use this is we first going to determine the period of the building using ASCE 7-22, which came out to be around 0.1 seconds. From this, we can read the spectral acceleration, which came out to be around 1.1 g. And from this spectral acceleration, we can then multiply it by the weight of the building in order to give us a shear demand needed for our assessment. And I'll bring it over to Jennifer, who will talk more about the process about the assessment and retrofit of this building.
Okay, now we can start with our assessment and retrofit process. This is going to begin with a Tier 1 screening, which is going to consist of 2 checklists. One for the immediate occupancy and the other for life safety, as Eric mentioned earlier. Within these 2 checklists, they are going to consist of a number of evaluation statements that the team will evaluate and determine whether an item is compliant or non-compliant. If an item is found to be compliant, then we will stop and no further analysis will be done on that item. But if it is found to be non-compliant, we will take those items down to a Tier 3 analysis where we'll look further into those non-compliant items. The same process will then happen here. If it is found to be compliant, then we will stop and no further analysis will be done. But if it is found to be non-compliant, those will be the items that will get taken down to a retrofit alternatives, where finally the team will be able to recommend the best suited alternative for Seattle City site. Shown is going to be an example of what these Tier 1 checklists look like. Highlighted in yellow, you'll see that it gives us the checklist type. This one shows the immediate occupancy, but like I mentioned earlier, we also checked the life safety. Also highlighted in yellow, you'll see that it gives us the building type. Our building is made out of precast concrete, so that's why we are using the PC2. And then shown are going to be the 3 evaluation statements that our team found to be non-compliant from our Tier 1 screening. These items had to do with the transfer to shear walls, which describes how our diaphragms, like our roots and our floors, are able to transfer those seismic forces onto our shear walls. Another item had to do with any openings immediately adjacent to our shear walls. And a third item had to do with our wall thickness. Because these were the only 3 items that we found to be non-compliant from our Tier 1 screening, these are the 3 items that will get taken down to a Tier 3 analysis, which Daniel will further explain.
So continuing with tier 3 analysis, we have the opening adjacent to shear walls. So here we are looking at the 3D representation of the office portion of the building. The lower level goes from 0 to 11 feet, and the upper level goes from 11 feet to 23 feet. In the middle, we have an intermediate office floor slab, which is our diaphragm in blue. And in seismic design, the diaphragm is an horizontal structural element such as a roof or floor slab that collects earthquake forces and transfer them into vertical lateral forces resisting systems such as shear walls. And in this case, the diaphragm has an opening, meaning it cannot transfer seismic forces uniformly into the shear walls. And when the building is experiencing seismic motions, the diaphragm develops inertial forces, which we denote here as FP, and the FP for this diaphragm is equal to 44 kgs. This force must be transferred from the diaphragm to wall collection along the effective wall length, and when we distribute this force along the available connection length, we obtain a shear demand of approximately 2.3 kgs per foot. Next, we evaluate the design shear capacity of the existing connections, which consist of number 5 anchors spaced at a RETROFIT. And from this configuration, the design shear capacity of this connection is equal to 4.7 kgs per foot, which is bigger than the demand, therefore making this item compliant. Now, Jennifer is going to continue with the next RETROFIT item.
To further analyze our wall thickness, we did an add plane check. To do this, we looked at our worst possible case section for the building, which was the west section. This is because the north and south walls are the walls that carry the weight of the crane. So we took the 37-foot wall, which consists of half diameter post tension strands spaced at 11 inches. And then we loaded the wall with the friction of the crane, the weight of the crane, along with the weight of the roof and inertia that we calculated. Given these forces, we were able to calculate our maximum demand, but this maximum demand does not account for the slenderness in the wall. So using an equation that does account for the slenderness, we obtained a moment demand of 12 kPa, which is on a per foot basis. And then to analyze the capacity, we took a 12-inch cross section of our wall panel, and we determined our capacity to be 13.6 kPa, making our capacity greater than our demand, making this item now compliant in our tier 3 analysis. Now, Lisa will further explain the last item.
So finally, in order to assess the transfer of seismic forces from the diaphragm to the wall, we're going to compare demand versus capacity. For demand, we're going to look at the roof plan. You can see we have two types, type 1, which is on the edges, and type 2, which is in the middle. We're going to load this with our seismic forces and observe the shear is going to happen in each type. From this, we came up with this shear diagram, from which we calculated a shear capacity for type 1 of 1.76 kPa per foot, and for type 2 of 0.83 kPa per foot. Now for the capacity, we got this table from the manufacturer catalog. When we plug in a specific configuration of fastener pattern, side span, and span in feet, we obtain a capacity for type 2 of 1.1 kPa per foot, which is bigger than the 0.83, which makes it okay. But for type 1, we only get a capacity of 1.35 kPa per foot, which is not bigger than the 1.76, therefore making this item non-compliant. This is the only item that was non-compliant from the tier 3 analysis, and therefore is the only item that we're going to retrofit.
As Lisa mentioned, there's only one item that is not compliant from our tier 3 analysis, which is that transfer load from the diaphragm into the concrete wall. So we will be only needing to do one retrofit for that connection between them. We will do this by installing a 6 by 3.5 by 1/2 L-shaped steel angle that is going to be held in place using screws that connect to the bottom of the steel deck, and also to the concrete wall. These screws and anchors are going to be spaced at an L-shaped steel angle. The orange circle is the screws. The purple circles are the anchors. Aside from our retrofit, we'll also be designing a platform. This platform is going to be used by the steel workers who will be standing on that platform to install the retrofit. We're going to be utilizing the crane by using the crane leg to place beams, and on top of those beams, we'll have our deck. Here's the elevation view of how the platform is going to look. In the green, we have the crane leg. On top of the crane legs, we will have 2x12s that will be sitting along the crane leg. And on top of those 2x12s, we have 2x10s that will be spaced 2 feet on center, and we'll have blockings between them that are also going to be 2x10s. On top of that, we'll have a 3/4 inch plywood that has the width of 16 feet and a length of 44 feet. And this is a small animation of how the platform is going to look.
So just to give a quick little summary of what we did, we first started off with a tier 1 screening. And from that tier 1 screening, we found 3 deficient items, which was the transfer to shear walls, the openings at shear walls, and the wall thickness. Because of these 3 items, we then took that to a tier 3 analysis. And in that tier 3 analysis, we found that openings at shear walls and the wall thickness were compliant. Meanwhile, the transfer for shear walls was non-compliant. Because of this, we then took that item into the retrofit phase, and from that retrofit, we created a retrofit, which consisted of installing the L angle to the metal deck and the concrete wall. And in addition to also that, we also designed a platform where the steelworkers can install the retrofit. In addition to all of that, we also created a cost estimate, which came out to be around $38,000, which included all the materials, labor, and anything else. Thank you for listening. Is there any questions? Yes.
Again, great presentation. I might have missed it, but what level of earthquake impact are you designing to?
So yeah, we'll be designing for a BSE 1N and a BSE 2N.
Which means?
So a BSE 2N means that there's a 2% probability that will be exceeded every 50 years, which is, I think, if I remember the math correctly, is like 1 out of 2,435 years chance of happening every year. And then a BSE 1N is like 2/3 of the BSE 2N.
So in layman's terms, if we had like a, I don't know, like they give us a number, like a 6.0 earthquake or a 7.0 earthquake, how does that equate to those numbers? Like, have you designed it to beyond those standards? Like, uh-oh.
As far as I'm concerned,
very rare one would include like the very high magnitude one, which is what we accounted for our design.
Okay, and then maybe your specs already factor that in, so when you're designing to that particular BS and whatever you said standard, that already is factored into that.
Yes.
Okay.
Yes. So I guess first of all, thank you for having some very clear presentation. I'm a surface water engineer. SEISMIC is really not in my wheelhouse. That was really easy to follow. Appreciated. My question for you all is with regards to uncertainty and factors of safety. In the world that I live in, I am accustomed to seeing structures, especially critical infrastructure, needing to provide multiples of resistance when compared to the design loading. And I'm seeing in your analysis that you're just talking about simply being greater, more resistance than the seismic calculations were indicating. So my question for you is, did you consider factors of safety that just didn't make it into the presentation? And if not, how would you go about it?
Yes, so throughout the whole design, we use an LRFD design, which already factors loads. And on top of that, we use an R factor of 3 as a like safety factor. Does that answer your question?
It does, thank you.
Any other questions? Thank you.
Yeah.
And I think comes fast and the rate is funding for solving so I think the solution. And it is not supposed to
All right, then. Hello, everyone. We are the Skagit County Culvert Replacement Group, CEE 26.5. I'm Micah. With me today are Matthew, Chris, and Riley. So a quick overview of what we'll be doing today. First, wanted to go over some of our background information, then our literature review, site investigation, alternatives and evaluation matrix, and finally our 30% design. Our team structure currently consists of Allison Sudley, Ryan Adams, Ken Hansen, and Emily Doreen as our project sponsors. We have our professors, Dr. G, serving as our project coordinator, and Dr. Lee serving as our faculty advisor. The four of us are currently serving as project engineers. So to start things off, we want to first talk about the Washington Department of Fish and Wildlife, or WDFW, Fish Passage Inventory. The WDFW tracks fish passage barriers across the state and identifies them as either total, partial, or non-barriers. This inventory aims to remove these barriers in order to improve ecological health, restore fish populations, and reduce flood risk across the region. Our site is located within the Skagit watershed and has been identified as site NC75, a partial barrier due to an existing culvert. Looking more into our site, it was previously privately owned by a local couple, but it has recently been donated to Skagit County. Skagit County plans to incorporate this site into the reopening of Hiawatha Big Rock Park, which is a hiking trail that's been closed to the public since 2010. As mentioned before, our site has a current culvert with a diameter of 4.5 feet and a span of 35 feet in length. This culvert has a slope of 2.2% and a smooth metal interior, which in turn is leading to fast and shallow water flow. As a result, a 2001 survey showed that this site only has a 33% fish passability. One last thing to note is that the culvert is currently showing some structural damage, which means water may actually be flowing outside of it. So this is important because our site actually has a drainage area of 1.25 square miles, and removing this existing culvert would actually restore 1.36 linear miles of upstream habitat for native fish, such as cutthroat trout, chinook, chum, steelhead, coho, and pink salmon. Shown here is a map of the surrounding area. As you can see here, water flows downstream from the total barrier to our site, which eventually continues to flow under State Route 9 before joining with Nookchance Creek. From there, Nookchance Creek flows north and eventually merges with Skagit River. So our objective is going to be to remove this existing culvert in order to improve fish passability, then restore the stream to its natural conditions. However, Skagit County would also like to preserve the crossing the culvert is currently providing, and has therefore asked us to evaluate some other crossing alternatives.
As part of our literature review, we looked at several different manuals. This includes the WDFW Water Crossing Design Guidelines, which helps us with stream restoration, hydraulic design, and determining a crossing structure. We also looked at the USGS magnitude, frequency, and trends of floods at gauged and ungauged sites in Washington based on data through water year 2014, which helped us estimate the volume of floods passing through our site. We looked at the WashDOT Design Manual to help determine bridge geometry, and then two AASHTO documents, the LRFD Bridge Design Specifications and the Guide Specifications for the Design of Pedestrian Bridges, which each helped us with different structural requirements for our crossing structure. Within the WDFW manual, we looked at 4 preliminary options for culvert replacement. The first one was a complete removal of the structure, which is the preferred method for stream restoration, but would remove crossing for pedestrians and wildlife, which makes it unsuitable for our site. We then looked at 2 different culverts, a no-slope culvert, which is flat, and a stream simulation culvert, which is sloped but mimics the natural channel bed inside of the culvert. However, both of these culverts block off the floodplain, the area where water flows under extreme weather events, and they do not tolerate any lateral movement of the channel. Based off of preliminary site research, we determined that both of these characteristics would be very important for our site, and thus we decided to proceed with our last option, a bridge. Bridges can be used on any size channel, and they're extremely flexible in design. Additionally, they do not obstruct the floodplain sitting above it instead, bringing greater riparian benefits to our site. Bridges are generally more expensive than the other options, but we determined that preserving the floodplain and allowing for lateral channel movement would be of great benefit for our site. Within the WDFW manual, we then looked at several requirements for bridges. This includes that we need at least 3 feet of clearance between the 100-year flood surface, the most extreme flood event we'll be analyzing for our design, and the bottom of the bridge. This is necessary so that any large debris passing through the site does not get snagged on the bridge and cause damage. Additionally, our bridge should ideally span across the entire floodplain. However, this is not always economically feasible in case the floodplain is extremely large. Under this circumstance, we may encroach into the floodplain, but we'll have to do several other checks to ensure that the bridge is still suitable for our site.
In order to make sure that we stayed in compliance with our bridge span and our bridge clearance, it was important for us to determine what our annual exceedance probability was for our 2-year and our 100-year flood. To do this, we looked at the USGS manual, which gave us the equation based on our flood region being flood region 3. Shown here in the equation, you can see the lowercase variables, which represents coefficients based on the flood region. You can also see the capital A, which is based on our area that we took from the watershed delineation. And the capital P is the annual mean precipitation, which we took from stream stats. With all of those, we were able to calculate what our 2-year was, which was 28 cubic feet per second, and our 100-year was 93.2 cubic feet per second. Next, we wanted to get an idea of our bridge geometry, so we took a look at the WSDOT design manual. There, we found that the minimum width was 8 feet, and we also looked at the railing height of 54 inches, which is used to protect bicycle groups. One thing to note is that this is not a WSDOT project, and so we only use this as a recommendation. We also looked at the AASHTO manual to look at load combinations and limit states. There, we were able to determine the 90 PSF pedestrian live load, as well as the H5 emergency vehicle load. We also were able to find out that our bridge must deflect no less than 1/360th of the entire span. If you look here, you can see a topographic map of our site. Looking closer, you can see exactly where our culvert is, which is underneath the trail within the embankment. Our trail specifically sits perpendicular to where our stream is. The trees you see here are a major site constraint that we will talk about later. And with the investigation of our site, our team used these 4 cross sections in order to determine our stream behavior. This cross section specifically, which sits directly upstream of where our culvert is where we use to model and find our bridge span.
As part of our cross-sectional survey, we first determined the elevation of the land with respect to the deepest point of the main channel. We then determined the separation between the bankful stage, which is the area where water flows under conditions inside the main channel, shown with the green hatching, and the floodplain, the area where water flows under extreme weather events, shown with the brown hatching. This separation is usually denoted by obvious grade breaks, as can be seen at the right border, where the floodplain is noticeably flatter than the main channel. With this channel geometry, we wanted to determine the shape of our 100-year flood to help determine the clearance of our bridge and the necessary span. To do this, we looked at several different empirical equations, including the bankful discharge equation. Bankful discharge measures the volume of water passing through the bankful stage of our channel. Within this equation, we found that the width of our bankful stage was 12.6 feet and the height was 1.4 feet. We then determined our slope using the longitudinal profile we made on the site, and we determined the median pebble size by recording the diameters of various rocks within our channel and graphing the result. Using all of these values, we determined that for this cross-section, our bankful discharge was 28.4 cubic feet per second. Using this discharge, we then applied that to Manning's equation, which determines the discharge of water passing through certain geometrical areas. Inside of Manning's equation, we know that A is the area of water, highlighted in blue, R is the hydraulic radius, which is the area of water divided by the wetted perimeter, which we have highlighted in red. We still know our slope from the previously mentioned longitudinal profile. Using all of these values, we were able to determine N, the roughness coefficient. In our case, we found that the bankful roughness was 0.021. The roughness within the floodplain is much different as water rarely flows there. We used tabulated values for heavy brush areas of 0.075. Using these roughness values, we then applied that back to Manning's equation, but this time with our 100-year flood of 93.2 cubic feet per second. Within Manning's equation, we still know our roughness and our slope, and our area and hydraulic radius can be expressed as a function of the water height. This allowed us to determine the shape of our 100-year flood as shown. For this cross-section, the height of the water was 2.73 feet, which is useful for determining the clearance of the bridge, and the width of water was 38 feet. Correspondingly, we would want our bridge to have a clear span of 38 feet. This is to ensure that we have a smooth transition from this nearby cross-section to the bridge's location, and to ensure that we are not encroaching into the floodplain.
Once we were able to determine our bridge span and our channel geometry, it was important that we looked at some alternatives. So our first alternative was a steel girder bridge. With this, we were able to figure out that it had easy construction as well as quick construction and a long life cycle. However, with this, may require a crane being brought on site, and also it has vulnerability to corrosion due to it being steel. Our next alternative was a steel truss bridge. With this, it had easier material components to handle when being brought onto the site, as well as it has a great strength to weight ratio. However, with the steel truss, the problem with this is a difficult construction and the labor-intensive upkeep of maintenance over time. Next, our last alternative was a timber girder bridge. With this one specifically, it also had a great strength to weight ratio, and it also had predictable fire safety. However, with it being timber, it was susceptible to biological attacks from the insects as well as decay from the water. With those alternatives decided, it was important for us to get an evaluation matrix in order to determine what our preferred alternative was. We got some criteria and weighted them and got approval from our sponsors. One of our first major criteria was environmental impact, which looked at little to no site disturbance, little to no toxic chemicals, and with this, the timber girder bridge won out over both alternatives. The next was constructability. There we looked at the ease of construction and the speed of construction. Due to the timber girder bridge and the steel girder bridge both being of the same design, they won out over the truss bridge, which has a more complex design. Our other major criteria was the upfront cost. There we wanted to look at the material costs, transportation costs, as well as labor for the bridge. Here, the timber girder bridge meet both criteria, or both alternatives in this situation. We also looked at maintenance, longevity, hydraulic capacity, public safety, as well as aesthetics. With all of these ranks, we were able to determine that our preferred alternative was the timber girder bridge. With this, it won out with a score of 88 out of 100 over the other alternatives.
Now moving into our 30% design, I'd like to dive more into detail about those site constraints that Matt talked about previously. Our main site constraints are these trees that sit adjacent to the culvert. Specifically this tree, circled in red, which is currently being undercut by the stream, causing erosion of the material around the roots. Our sponsors anticipate that this tree will collapse or be cut down during the construction process, so they will not look to preserve it. However, they would like to preserve the trees just behind it to the left of this red line. In order to do so, we will be placing one of our abutments in line with these trees to prevent undercutting. Here is a plan view of our site with our proposed bridge location in the orange hatch. Our north side abutment will be in line with the edge of the floodplain. Here are those trees that I just talked about, with the tree that's currently being undercut highlighted in the red dot. We will be placing our south side abutment in line with those trees behind it to prevent undercutting and erosion. Moving on to our bridge design, I'd like to highlight some of our bridge geometry. We consulted with our sponsors over the size of the vehicles they would need to pass over the bridge and arrived at a width of 5 feet. We will be using railing height of 4.5 feet to ensure cyclists don't fall over. Using the NBS wood design manual as well as the AASHTO load cases, we sized our wooden girders to be 12.25 inches wide and 18 inches deep, and we'll be using glue laminated yellow cedar. We will also be using 3x12 wooden beams that span across the bridge as our decking. And our bridge will be 40 foot in span. Here is the current condition of our site. Our trail currently has a 6% slope that goes down to the location of the culvert. We will need to excavate this region about 300 cubic yards of fill to remove the culvert and restore the stream to the natural condition. We intend for our bridge to be at a level grade, so we'll need to fill this region to ensure that the bridge and the trail are at the same grade. Going further into our bridge design, like I said before, our bridge is 40 foot in span, a little bit longer than our Q100. to account for climate change, as well as ensure that our south side abutment is in line with those trees. Here is our Q2, or the height of our ventral discharge, and then our Q100, which sits 5.9 feet below the bridge superstructure, which is well within the WDFW clearance requirement of 3 feet. We do not have a geotech report on the site, so you will be working under the washout assumption that the scour line sits 3 feet below the ground surface, and our foundation must sit 2 feet below this line, or a total of 5 feet below the ground surface. Thank you for listening. Are there any questions?
Oh, why not? Great presentation on that. Just for the lay people in the room, can you explain what a culvert is? And were you guys taking any field sampling? I think you like measured rock sizes, but was it a combination of field sampling with planning for the flood, out of your flood?
So yeah, so just to clarify your question, you're asking what a culvert is, just to be clear for everyone. And then also, did we use any field samples? So to answer that, culvert, yes, maybe we should have explained this in more detail. A culvert is just we have a little metal tube on site that water is passing under. There's a large trail above it that the owners used for crossing this stream. And so the culvert is just causing too shallow of water for fish to swim through, and that's why it needs to be replaced. As for if we have any field samples, actually that's been one of the major challenges with our project is we have no geotechnical report on our site. So especially at the end when we started showing some of the scour calculations, those are assumptions made in washout, but they're not detailed enough to go to a practical design. A lot of things that would be done in more in-depth designs would require a geotechnical report, which we were not able to get. A lot of our problem was that this was a privately owned land before. It's very new that it's been transferred to the county, so a lot of information was lacking at the beginning of the year, and we had to get around that.
So is this like a feasibility study level, and then those field data will happen further down the line once the project goes forward?
No, the county very much wants to proceed with this design. It would just be more that this is kind of a high level design, and some of the more specifics, especially the structural stuff, is going to require some more detailed investigation from professionals that we are not licensed or experienced enough to give.
More questions? So the purpose of this project, it sounds like, was for accommodating fish passage or improving that condition. In your design, as you were looking at the bridge, did you account for include any recommendations for restoration of the stream bed area? What does that look
like? So where the culvert sits directly, we were told by one of our sponsors that the culvert could be removed and the stream itself should be sufficient. We did look at the stream restoration a little bit, determining what pebble size would be needed to replace it. However, we did not go into the entire design of it.
Add on to that, there's also a natural rock wear that sits just below the culvert. So due to that rock wear, that is one of the main reasons our sponsors think that the stream will just naturally be restored. There's no necessary work to be done for restoration.
I don't think I fully tracked the Manning's calculation that you did based on the Q bankful width. It sounded like you used a regression equation to figure out what your Q was, and then you took Manning's equation and backed out Manning's N. Is that accurate? An accurate understanding? And I guess follow-on question would be, did you double check kind of literature values for your final answer? It can be really hard to estimate Manning's N in an open channel in a natural system.
Yeah, so that's a good question. So yes, you described the process accurately. We used our bankful discharge. That's as an empirical equation to help estimate our Manning's N. And then, yes, we did do a number of checks to sort of ensure that it made sense. We looked at some literature values. We compared it to other locations in the site. And we also looked at how the water elevation For example, one of the things we made sure of is, does our baneful discharge, does it lead to or is it similar to what our 2-year value, because general trends are that the 2-year flood will be roughly equal to your baneful discharge. So we did a number of checks like that. And with our sponsors, we double checked all of them that they would seem reasonable to our sponsors. Another thing is that in the end, we didn't do anything to make sure that our roughness value was super accurate, because our sponsors may not actually excavate the exact channel we design. Our sponsors had some tendency, a preference for simply removing the culvert and allowing the water to simply shape the channel naturally, which was feasible due to the rock weir just below our site. And so as a result, it was not, we created a suggested design on what we thought it would look like, but it is not particularly less necessary to create something incredibly accurate for this level of design.
Hi, I was just wondering what made you decide on Woodland, and if you looked at anything different, such as simple heat treatment.
Yeah. Was the question like why we looked into glue lamp?
Yeah, like if it has any advantage over other alternatives.
Yeah, so glue laminated beams sort of the best for our environmental impact category. It has the least chance of being affected by biological attacks from insects and from water decay.
I saw another hand going up.
I have a similar question.
Okay. Any other? Okay, thank you. That's the first question. And I like to see this off. I like to recognize one even who are elected. He's doing a great job of running the entire show. I am here for the talk. Okay, so we'll take a break and we'll do that for some 30 minutes. Oh, yeah.
Well, Like dying. Did I walk away? Yeah, that's how I might watch that one together. Where you are.
But it's not for. I didn't. Mais c'est quoi c'est pas comment expliquer. Ça connaît que s'il y a que la mission, c'est pas comme si t'avais ça. It's only 2 hours, so I haven't got No, it's not just a good one, right? Fuck is really still going. Non, fait que je suis convaincu que c'est complètement. Il y avait une France, le bureau de ma voiture se retrouve assez prendre une barrière. Donc j'ai peur que ça arrive à son Transportation.
Oh, really? Still want to get to the here. Yeah. And most of us is so like it's
I would have to never
Yeah, I gotta go. I've lost some weight. So anyway. So they were yeah, but it's pretty good. Yeah, I know. We're trading class. I might have been like I find it's just like okay.
Certainly.
Yeah. Anxious to find it out. I was able to send out. A lot of stuff. Yeah, that did happen. When you. Yeah.
Thank you. So now we move on to our second session, and we are going to start out with a project that was sponsored by KPFF Special Projects Division and Vigor. And KPFF has sponsored a few of community benefit projects in the past. So I'd like to thank them for their continued support. And before I give it over to the team, I want to recognize the team. As most of you would know, every year we, on behalf of the American Society of Civil Engineers at the Seattle section, we run the presentation competition. And the presentations are judged by 5 professional engineers, and the team that comes at the top gets to present at the May Seattle section meeting, ASC Seattle section meeting. So this team was selected this year to be the top team. And with that introduction, over to the.
Hello, everyone. Thank you so much for being here. We're Civil Engineering Team 26.2, partnering with KPFF Consulting Engineers to design a stormwater treatment and conveyance system for our client, Vigor Shipyard. My name is Tamara, and my partners are Mira and Shao. We will begin with an introduction of the team, and then we'll go into our background and problem statement. We will then go into our project goal and our alternatives, the 10% design of the alternatives, how we determine the preferred option, and then the final proposed solution at 30% design. So here's the team. We have one liaison from Vigor Marine Group, Dan Keene. Thank you for being here with us today. And we have 3 liaisons from KPFF, Scott, Calvin, and Megan. Thank you also for being here with us. Our faculty advisor is Dr. Mike, and our project coordinator is Dr. G. Big shout out to them too. And Mira, Sham, and myself are all project engineers. So a little bit of background about Vigor Marine Group. Vigor is a private shipyard located on Harbor Island in downtown Seattle's industrial district. Vigor works on manufacturing, cleaning, and servicing large marine vessels operated by the Navy, the Coast Guard, and Washington State Ferries, fishing vessels, and more. It occupies 29 acres in the northwest corner, shown here. And Harbor Island is 420 acres. So our problem statement, Washington State's piers currently drain untreated stormwater into surface water, such as the Puget Sound. Therefore, we have been tasked with designing a system to collect and treat stormwater from Vigor Shipyard's piers to prevent common stormwater constituents from entering Elliott Bay.
All right, so here's an aerial view of the site. Essentially what you're looking at right now is an area highlighted in blue, which represents the area in which stormwater is currently being treated. Basically, there is a drainage system that conveys all the water to the detention tanks right here, and there is a treatment system on site. The areas highlighted in yellow, which represent piers, are the areas that are untreated. Why they are untreated? Because the piers were built before, they were not built with a stormwater collection system. So instead, they drain directly into the Puget Sound. And we want to mention that we have 4 piers operating at Vigor currently, but for the scope of our project, we only focusing on Pier 3 and Pier 4. So a component of a pier basically have piles. Piles are just these supporting structures. On top of piles, we have pile caps, which are basically rectangle blocks, and then we have deck panels, and the spacing between deck panels is called cavity. So here's a profile view of Pier 4. Pier 4 is at an elevation of 19 feet. We have the piles right there. We have the pile caps, these rectangle blocks, and then we have the deck panel, which is 3 feet. And high tide, it can reach an elevation of 11.36, which is one of our main constraints because the pipes cannot descend below that. And here's a view from below of Pier 4 again. These are the deck drains, and that's how they currently drain directly into the surface water. We have the C-shaped deck panels. We have cavities and pipe hangers, which will help support the pipes. And we have existing utility lines as well. So here's Pier 3. Pier 3 has 2 sections, an old section and a rebuilt section. The old section has 666 deck drains. The rebuilt section, which is graded, has 5 deck drains. And similarly, this is Pier 4, highlighted in yellow. To the right is a dry dock. Pier 4 has 480 deck drains, and it has a platform which connects to the catch basin. So, jumping into our proposed alternatives, the goal of these proposed alternatives is to design stormwater conveyance system for piers. So briefly, I'm going to describe option 1, option 2, and option 3. So for option 1, actually for all 3 options, we're going to collect, the water will be collected through deck drains and then conveyed through pipings. So briefly explaining option 1, the water is collected and sent to the nearest catch basin, and from the catch basin, it can reach directly, it can be conveyed to the existing treatment system. Option 2, instead of conveying it to a catch basin, we are going to convey it to a wet well, and then the water will be pumped to an upgraded treatment system that has been chosen. And option 3 is quite different from option 1 and 2. Instead, we're going to treat beneath the pier. That's where the treatment unit will be placed beneath the pier, and that's how the treatment operates.
So now that we have outlined all our alternatives, this is a checklist for how we will move forward with 10% design. That begins with selecting the treatment system for our stormwater. Then to simplify our conveyance and piping, we will close a portion of the deck drains. Then route the pipes, determine their locations, and how they will then be routed to our collection system. So to begin, we have main constituents being heavy metals. This includes zinc, copper, lead, and as well as total suspended solids, the pH of the water. We wanted to say Vigor does a great job of managing the constituents on site with sweeping and best management practices, but this is largely impactful to the aquatic environment nearby, and the introduction of these contaminants can be very harmful to our precious coho salmon as well as the vegetation and water quality. So in order to treat this water, we will move forward with these treatment systems. All options are approved by the Department of Ecology. We will determine the amount of water that comes off of a pier that needs to be treated with the Western Washington hydrologic model, and then partnered with the amount of water that a treatment system can handle, we will determine how big or how many units we need. Our first option here is the chemically enhanced sand filtration system. This is that on-site treatment unit we've discussed. Our second option is a filter media bed, which is an equipped system that's about the size of a trailer and will be placed on shore. And our third option is an Atlan flow filter, which is cartridge-based unit and about the size of a catch basin. So in order to get the water there, I mentioned we need closed deck drains. We're seeing here a plan view and section view of a deck drain. A storm event will happen and the area surrounding a deck drain will fill with water and then flow over the edges as seen here. We've modeled this with the Santa Barbara Urban Hydrograph and then compared this flow to the capacity of a deck drain, which was modeled with the Weir equation. Our main design constraints here are the ponding depth on the pier, how much water that was given to us by our sponsors. This includes a spake factor of safety of 2. By closing deck drains, we increase the area surrounding the pier, therefore increasing the flow that enters a deck drain. We've done this iteratively until we've concluded we close 5/8 of the deck drains and ensure that the capacity of the deck drain is not exceeded, as well as that the ponding depth on the surface of the pier is not exceeded. So there was that situation with the 5 deck drains on Pier 3. We have taken a look here at the grading plans that currently exist on this section. The highest point here at the ridge line after this is overland flow to nearby catch basins. And to simplify our conveyance, we've decided to change the current grading plans where it's gently sloped toward those 5 deck drains. We will regrade this section, raise the south end elevation to 18.01, and then match that overland flow so that this section will travel, the water will travel to the nearby catch basins.
Okay, wonderful. And for the old section of the pier is where we will be designing the pipe conveyance system. So we have a few constraints, main constraints for the pipe conveyance system. One is that pipes cannot descend below the high tide at 11.36 feet, or else they will be submerged by salt water. Another constraint is that pipes cannot descend below the invert elevation of the catch basin, otherwise water could backflow into these pipes. The way we sized our conveyance system was using Manning's equation with a roughness coefficient for HDPE pipe. We first sized the lateral pipes shown here in the deck panel cavities, which collect water from the deck drains. And then we sized the trunk line, which will be attached to the edge of the pier and collects water from the lateral pipes. We used a hand calculated flow from a 100-year storm as mentioned previously. And we sloped these pipes for gravity flow at about 0.5%. The result was 3-inch lateral pipes and an 8-inch trunk line. So for our first option for piers 3 and 4, what you see here as the arrows are pipes, the red pipe is a trunk line which connects the main trunk line which connects the water to the shore. So a continuous trunk line was explored, but the elevation loss was too great. So we decided to place these blue longitudinal pipes within the deck panel cavities to preserve elevation. From there, these blue longitudinal pipes connect into the trunk line as well as the green lateral pipes, which also collect water from deck drains. And then eventually the water ends up on shore at a catch basin, which is connected to Vigor's existing storm drain system and gets treated at the Kaido Sand Enhanced Sand Filter upland. The second option features a similar conveyance system to option 1, but instead of reaching a catch basin, the water reaches the shore and enters a wet well with a pump station, which pumps water to an at-grade treatment unit shown here in yellow, and gets filtered through a media bed and then gets discharged back into the Puget Sound. The third option is the below pier treatment units shown here. We have the blue longitudinal pipes bringing water into those, and there is no trunk line because the water never actually reaches the shore. It gets treated and discharges into the sound. So the treatment units will be placed below deck panels. They're about 5 feet tall and 4 feet wide. We've consulted KPFF structural engineers for a cost estimate on the structural update that this will require. And as a reminder, this is what they look like.
So now that we have completed our 10% alternatives, we have created cost estimates for all three and compared them here. As you can see, one of the biggest cost drivers for options 2 and 3 is the procurement of the treatment system. And another cost driver would be the trenching that is required if the water is traveling to shore. So that's reflected in the paving and trenching and the treatment. In total, our least expensive option was option 1 for both Piers 3 and Piers 4, and option 2 was our most expensive. So we've compared all of our alternatives, including the costs with operation and maintenance challenges, as well as the disruption to operations, what would require Vigor to stop operating, and the treatment performance, the compliance with these anticipated regulations, and also how the water will be clean at the end. So here is Pier 3 with a completed decision matrix. As you can see, option 1 scored favorably high in all categories, and option 2 and 3 was a bit lower. So we've decided to move forward with 30% design on option 1. Similarly, for Pier 4, this is the decision matrix. Option 1 scored the highest in these categories, and we have decided to move forward in our 30% design for option 1 on both piers.
So for our 30% deliverables, we are going to have CAD drawings and hydraulic analyses. So for our CAD drawings, we have a plan view, which is just like a view from below, showing the pipe layout network and the location of the catch basins. For profile and section views and profile views, we're just saying how the pipes are sloped and where the catch basin is located and their elevations. And for section views, is a cross-sectional view of the pipes. For hydraulic verification, we're using Appendix F of the City of Seattle manual, just to ensure that scar velocity will be reached. And we're also ensuring that the pipe will not flow even when they can be surcharged.
So you can see here that we have completed this analysis. We used hand calculations for our 10% design, and for our 30% design, we verified this with a continuous hydraulic model, called the stormwater management model. This is referred to as SWIM. We identified critical locations, which are here, and ensured that the scour velocity, which is the velocity required to pick up any bits of sediment or grit in the pipes, is reached in all of these locations. Here we have a profile view of the Pier 4 trunk line. We used, as Shem mentioned, the Appendix F in the City of Seattle Stormwater Manual and used their design storm. Here we confirmed that there's no flooding above the grade, so our pipe sizing is successful and we can move forward with our 30%.
In summary, we've created a 3D rendering showing the pipe locations. So you can see the blue longitudinal pipes in the deck panel cavities, which connect into the red trunk line, as well as the green lateral pipes connecting into the trunk line. We have a full 3D model at our poster, and we have our 30% CAD drawings as well. So if you would like to see those, please stop by. We're on the basement. We'd like to thank you for coming today, and we're happy to take any questions.
Did you do any hydraulic analysis and verification for Pier 3?
Thank you so much for the question. The question was, did we complete any hydraulic analysis for Pier 3? We definitely did. Here we have our options. Let's see if I can get to my video. We did the same process as we did for, it does look like I've stopped sharing, unfortunately. Apologies for that. But we have a nice little video of modeling that pipe design network that we preferred. It's outlined on our poster, and created that same design storm and made sure that the water doesn't flood above grade. Here we go. Just down a bit. There's Pier 3, and then we have a video right here.
Yes, sir, in the back.
I have a question. In option 2, which was above grade treatment, was it ever discussed with the sponsor of turning that into some sort of public display of showing this is how your water gets treated?
Thank you for the question. Great question. The question was, did we consider turning the at grade treatment media unit into a public display for people to see how the water gets treated. We have not discussed this, primarily I think because Vigor is a private shipyard, so it is not open to the public. Thank you. Yes, Lola?
What was the most challenging part and the most rewarding part in project?
I guess we all have different challenges. My main challenge was to basically screen the technologies because there is a whole list of technologies online, more than 100. So finding out which one best fits this industrial site was one of the best challenges to me because screening them all and then describing one by one, going through one of them and then finding the best one was the most challenging because it was a lot.
I think one of the most challenging was just the iterative process of determining where our pipes should go. We originally, as Tamara mentioned, explored a continuous trunk line and we're kind of defeated when we thought that wasn't going to work. We might have to place a pump, we had a few other alternatives, but using that cavity space and being able to utilize a few different collection options was challenging, but then at the same time, the most successful and most gratifying to get that all to work.
Yeah, I agree with both Mira and Shem. Probably the pipe placement was difficult, but it was very rewarding to see our hydraulic results and analysis confirmed and confirmation from our sponsors. Thank you. Yes, Hiram.
Understand why option was so bad, but can you explain to me like on 5 why option 2 was almost as bad?
Are you talking about our decision matrix? Thank you for the question. I wouldn't say option 3 was horrible, but it did score lower. So you're asking why option 2 scored or for this one they're the same, but scored low. Well, for one, it did have the costs were expensive because of the procurement of the treatment unit. So that includes like delivery, installation, markups. The operation and maintenance, the filter media bed does need to be replaced and it requires additional monitoring from Vigor employees. And then the disruption to operations, it would require excavation to install a wet well with a pump station, which is a lot of excavation that includes an electrical upgrade and repaving and sediment backfill. And then the treatment performance, the option 1 just scored the highest because it's a reliable method that's already been used by Vigor and not quite as tested for our site as the other 2 options. Thank you for the question.
Any other questions? Hearing none. And the project is named Operation Woodland Water Bed, and to hear more about it from the team. And the project itself is sponsored by Quantum Consulting Engineers. So I'd like to thank Operation Woodland Warm and Fed for the project idea and Quantum Consulting for providing the financial support and for providing the engineers to mentor the team. So with that, we're going to do.
Thank you, Dr. Chi. Hello, everyone. We are Team CEE 26.3. I'm Katie, and with me are my teammates, Mike, Pablo, Landon, and Nick. And we are doing a retrofit of the Lake Creek house. Just to give you an overview of what we're going to present about today, first we're going to go over our team structure and then give you some background to our project sponsors as well as our project site. And then we're going to go over some of our evaluation and analysis. And then we're going to get into some of our problem areas and retrofit solutions. And then finally go over our cost estimate and our next steps so that our sponsors can get this project going.
This is our team structure. First, we have our project sponsors, and we have Michael and Lottie Cervic from Operation People Moves Bed. We then have our project liaisons, where we have Max and Sandro from Quantum Consulting Engineers. And our project coordinator is Dr. G from Seattle University. And our project advisor is Brian from Atlas Design Group, and we are the engineers. Before we dive into the technical side of our project, I would like to give you guys a quick background of Operation People Moves Bed. Operation People Moves Bed is a nonprofit organization that was founded in 1995 by Michael Cervic. And the organization focuses on helping out those in need by providing them with warm meals, snacks, and clothing, as well as blankets in the winter. And they meet every Wednesday at 7:45 a.m. to help out the community.
Here we have a map of Tacoma showing Michael and Dottie's current residence in relation to our project site. The main reason Michael and Dottie want to leave their current residence is due to an increasing level of violence in the area. And the house that our project site is focused on is a two-story light-framed house, originally constructed in 1894. As for our problem statement, Michael and Dottie asked us to do two things. The first one being to evaluate the existing settlement issues they see within the house. To do that, we are inspecting the first floor framing as well as the foundation below. And now we're providing retrofit solutions to those problems. The second thing they asked us to do is make the house wheelchair accessible. To accomplish that, we designed a ramp entrance on one of the entrances of the home. And now Katie's gonna go into our site plans.
So because our house is over 100 years old, there wasn't any existing site plans. So after doing a few site visits, we drew up our own in AutoCAD. On your right, you can see our foundation plan, and on the left is our first floor plan. We broke up our plans into 3 sections, the first being the bathroom and the porch, second including the kitchen, and third being the living room. The living room actually has a second floor above it, but it's not part of our scope of work, so it's not depicted here. And section 3 is the only thing that is a part of the original house. Section 1 and 2 were later additions. Getting into some of our calculations, for our live loads, we used the IVC to find all of our live loads in the house. You can see they're highlighted in the green box. And then we used ASCE 7-22 to find all of our dead loads in each room of the house. And we broke this up into 3 sections, our first floor, second floor, and roof. We have 4 main problem areas that we're going to talk about with you today. The first being in the kitchen, which I'll hand off to Pablo to take.
The first problem area is in the east wall kitchen foundation. And this is what we believe the framing and foundation used to look like. We used to have posts sitting on top of their own individual foundation footings. And these foundation footings would sit on top of a compacted backfill. And that backfill was held by a retaining wall. A portion of this retaining wall is made of cinder blocks, and the other portion is made of wood. But over time, the wooden retaining wall began to fail, and some of the backfill started to slip away. And we believe that due to that backfill now missing, some of those posts lost their foundation footings. And behind this wall, there's also more backfill, and that backfill is pushing against the wall, and some of those posts have shifted inwards, and it's creating misalignment in the structure. This is our proposed solution, where we plan on replacing the individual foundation footings with a continuous footing. This continuous footing would be 7 inches by 22 inches, and above it, we'll replace the post with a CMU wall, and the CMU wall is constructed of 8-inch blocks. And the reason we're replacing the post with the CMU wall is because the post has been in contact with backfill, and that backfill has created a lot of moisture damage to the post. And the CMU wall has to extend above the exterior grade at a minimum of 6 inches, and the bottom footing has to sit below the interior grade at a minimum of 12 inches. Now, Luke is going to talk to you guys about problem area.
Yeah, so the second problem area that we'll cover encompasses the kitchen and the living room. So on our initial site visits that we took to the house, we noticed that there was some significant sloping and serviceability issues all throughout the first floor level of the house. However, most especially throughout the kitchen and the living room. Noted here on the image on the left and the floor plans on the right are the high and low points within this section. We took some measurements and found that there was about a 5-inch height change but then the high and low points were about a 4.2% slope. Due to this, we inspected the framing that lay below this section. So here's an elevation drawing of this section. You can note the correlating high and low points from the flooring. It is also important to note that the kitchen was a later addition to the house and is why the primary beam that is running the length of the house is comprised of 2 separate beams. We believe that over time, the post shown there in the middle began to rot at the bottom, causing settlement of the flooring and the beam above. The homeowner noticed this as well and installed a post shown there on the left. However, the second post continued to settle, leaving a 2-inch gap between that post and the beam. This caused wider separation between supports of the beam, causing heavier loading within the beam, as shown by the crushing above post number 3. So here's a real-life image of that 2-inch gap and the crushing within the beam. So because of this, we proposed to install a new post at the section of the 2-inch gap. Using the national design specification for wood construction, we were able to design this post to be a 6x6 Hemfer post. Using this adjusted compression capacity equation, along with these adjustment factors, we were able to get a demand capacity ratio of 0.77. Anytime a demand capacity ratio is less than 1, that means a member is sufficient for the loading seen at this point. Along with the post, we needed a footing to prevent further rotting at the bottom of the post and to also spread the loading down to the bottom of the soil. So with the loading seen at this point and dividing that loading by the soil bearing capacity, we were able to get the dimensions of this footing to be about 1 foot and 7 inches square minimum. Furthermore, we did calculations to reinforce this footing and found that 3 number 4 bars were sufficient. Our last solution was to install a new beam to address the crush beam. So using the NDS once again, we were able to design a 6x6 dug fir beam. And then to address the discontinuity of the 2 beams, we are proposing to install a face mount hanger to make this one uniform beam. So here are some detailed drawings of our solutions, noting the footing, the connection to the post, and another set of drawings with our face mount hanger and the new beam. So now I'll pass it on to Landon to talk about problem area 3.
Problem area number 3 covers the bathroom of the house. We believe there was a late addition to the home in the 1970s. And as soon as you enter the first floor bathroom, you see more sloping, this time towards the east wall. This led us to investigate the framing and foundation right below. And when we got to the crawl space, we saw significant moisture damage. The most important thing we saw was rotted sill plates that got completely crushed, as well as missing anchor bolts. These are important as they pose life safety issues in the case of a seismic event. And here is a picture of what is below the east wall. Note all the moisture damage and the crushed sill plates. For our proposed solution, we are proposing anchor bolts to get installed, as well as replacing that sill plate. The anchor bolts are important as they help secure the framing to the foundation, as well as help the house resist lateral loads. And the sill plates will be pressure treated to prevent moisture damage from occurring, like we saw previously. Here's a more detailed section view with all the callouts addressing the issues I just mentioned. The first one being the pressure treated 2x6 sill plate, followed by our anchor bolts, spaced 4 feet on center. And finally, we're going to be repairing the sheathing that got completely rotted out with new waterproof sheathing. And now Mika is going to talk to you about problem area number 4.
All right, so moving adjacent to the bathroom, there are also present issues with the back porch of the home indicated there on the plans, and this will be the final problem area that we cover. So this porch was the most recent addition to the home sometime in the 90s, and over time it has been subject to significant moisture exposure due to the lack of protection along the west facing side indicated in the box. So this has led to the deterioration of many of the framing components of the porch and has overall compromised its structural stability. This posed a challenge for us. As we know, Michael and Dottie do desire wheelchair accessibility into their home, so something we needed to consider was whether or not the current framing members would be able to withstand additional loading from either a porch expansion or a ramp system being added on. So taking a closer look at those members, you can see that they're in pretty poor condition. We have some significant deterioration along this top beam here, as well as some poorly connected stud supports. You can see that there are some nails sticking out along the top. There are also no anchor bolts holding the foundation, framing to the foundation, so that would be something that we need to consider as well. And there's also some cracking along the foundation itself. Something we considered was whether or not this cracking was due to potential frost heave. So typically foundations are built to extend below what is called the frost depth, which is that upper portion of soil that is subject to expansion and contraction over time due to the freezing and unfreezing of the water in the soil. However, in our case, the porch foundation is very shallow and is more or less just resting on top of the soil surface. So that could be why we're seeing some of that cracking. It could also be cracking due to settlement. We will not be able to find out without conducting a geotechnical review of some kind, which is outside of the scope of this project. However, ultimately, it is a problem that needs to be fixed, which leads us into our solution for the porch. So we are proposing a full removal and rebuild due to the level of deterioration that we're seeing within the porch. So this would involve first having some type of localized shoring to hold up that area of the house while we remove the existing members of the porch, and then having a new footing be implemented to extend below the frost depth. After that, we would be suggesting that all new wood pressure treated members are implemented. So this would involve replacing the sill plates as well as replacing that beam with a double top plate, replacing all of these studs and joists, and then also incorporating new plywood sheathing along that west facing side. And then finally, having anchor bolts to secure all of that new framing to the new foundation. Regarding wheelchair accessibility, we are proposing that an aluminum ramp extend from the south end of the house rather than the north end, which is where the porch is. This would be so that wheelchair accessibility is not contingent on Michael and Dottie first replacing all of those porch members that I just went over, as that is a more labor-intensive and cost-intensive retrofit. So like I said, this would be an aluminum ramp, and it would also be pre-engineered to make it easy to install. It also is adjustable to combat minor settlement over time. There would also be, we're also suggesting that a concrete walkway extend from the south end of the house to the north end, which is where Michael and Dottie park. There is an existing concrete walkway, however, we are suggesting what is on the screen right now, which is longer, to extend the full length of the house, and it also needs to be wide enough to have wheelchair accessibility, so we are suggesting that it be 3 feet minimum. So that will cover all of our problem areas and retrofit solutions, and I'll pass it on to Katie for the cost estimates.
So for our cost estimates, we broke it up by retrofit solution and then assigned a priority level to them. Priority level 1 meaning that it addresses a life safety issue or is something that is pertinent to them moving into this house. And priority level 2 is our rapid walkway due to this not addressing anything life safety, but is necessary for them in the long run to have accessibility to the house. And priority level 3 is our porch. This is because the porch doesn't include any life safety factors and is not necessary to have accessibility to the house due to the ramp being connected to our other entrance. And we broke up our costs to materials, which is the set value, and then labor, which is a range of values. Due to the house needing to be jacked up and temporary shoring being put in order to fix a lot of these things in the house, we wanted to provide a range of solutions so that we don't underestimate any of the costs. And this leaves us with our total on the bottom right of your screen. And we understand that this is quite high, so to help them to make these solutions come to life, if you guys are able to, please donate to Operation Keep Up Farm Fed. They're a great organization, and Michael and Dottie do a lot for the community out in Tacoma, and we wanted to do something to give back to them. So if you're able to donate, if you scan the QR code, it'll take you to their website. You can click that donation button, which will take you to a PayPal link where you can donate. Any amount is greatly appreciated just so that they can get this project moving and they can have a safe place to live. And with that, that concludes our presentation. Thank you for listening. I will open it up.
So for a post in problem area number 2, what was your deciding factor on making a time for? Was it much efficiency? Did it just make more sense, or was it just more cost effective?
We chose Humper because it was the most cost effective because it was going to be a treated post. We know that Humper is a little bit cheaper when it comes to. Thank you for the question.
So it looks like you addressed a lot of the accessibility on site, but maybe taking a step into the public space. Were there any wheelchair accessibility concerns with some of the surrounding, maybe pavement or right of way, pavement heaving, cracks in the sidewalk, things like that? Did you notice anything, steep slopes that would maybe impair some of the accessibility to the property?
There are some with the existing concrete walkway along the west side of the house. It would need to probably have some minor landscaping to be able to implement the longer concrete walkway that we are proposing. Other than that, it's not anything that is seeming too severe in terms of what you're saying, like severe cracking and like I guess heavy slope changes, if that's what you're alluding to. And then with regard to entering the house from the other areas of the property, I feel like we didn't notice anything to not allowing wheelchair accessibility, if that makes sense. So, thank you. Yes.
For that area 1 where you're looking to replace the foundation well below grade, how much of the cost of that is supporting the house while you rip out the underside of the foundation there? Like, did you guys look at the means and methods to pull that out?
Yeah, so for problem area 1, it's definitely it will be a little difficult since it is also along the property line of the house, that east side of the house. And so that is also something that would need to be taken into consideration while the house is being temporarily shored in that area. We do think that it would be better to start with that area of the house, not just jacking up the entire house at once. But that is something that would need to be considered. It's also that how close it is to the property line. Did I answer some of your question, Sarah?
Were there certain areas of the house that you weren't allowed to like explore or like investigate because of how severe the damage was?
Yes, in section 3, the crawl space, the grade came to waist level, and it is already hitting our heads. So you would actually have to crawl through the crawl space to investigate section 3. But from what we saw, just from shining our flashlight and looking at the foundation under the post in section 3, we didn't think there was any significant damage, especially compared to section 2, as the foundation's just not there at all, which we were able to access pretty easily.
Any other questions? Thank you.
Now we move on to our last presentation. This project was sponsored by Woodland and this is the first time we are sponsoring a project by project sponsors. So with that, I think to what the
This was brought up, I think, that they have.
I'll start again.
Good.
Just want to say thank you to all the parts who was watching our project. Thank you to Megan and Katie, our liaisons. Thank you to our faculty advisor, Colin Board, for answering our numerous questions. Thank you. Most importantly, thank you all for coming out to support and watch us. Without further ado, welcome everyone. I'm Colette, and with me are Paolo, Davey, and Francis. We're Team CE 26.6, and today we'll be talking about green stormwater infrastructure design and Woodland Park 2. Just a brief overview of what we talked about today. We'll go to the introduction, highlight the project goal, go into the site background Woodland Park 2 as well as a brief history. We'll finish it off with our design alternatives and how we reach them, finish it off with our final recommendations for Woodland Park 2.
For our introduction of 14, we're gonna have our two variations, Katie Van and Megan Singh. Our program advisor will be Colin Bond and project coordinator will be Dr. G. And throughout the school year, we'll have 4 project managers. To talk about the Green Stormwater Infrastructure or GSI, it is a stormwater investment that helps mimic the natural environment and helps localize the collection, infiltration, and treatment of said water. There are some community sites that the zoo currently is using, such as the former asphalt at Forestry shown in the left picture, followed by the rainwater at the Forestry also in the middle picture. And finally, we have also a constructed wetland at the Penguin exhibit.
Our main goal for our project is to increase GSI at the zoo. This is in part inspired by a waterworks study the zoo conducted in 2023. And as part of the zoo's overarching mission to inspire to promote conservation and sustainability and provide community education. The zoo also wants to mitigate combined sewer overflow events, which stems from stormwater runoff escaping the zoo. This is part of their 5-year sustainability plan and a goal to implement 3 CSO reducing projects. Lastly, we wanted to evaluate the ADA compliance for the zoo, for the bear lot, and to make additional recommendations as part of that evaluation. Some side background for our project. I think Woodland Park Zoo was founded in 1899 as a nonprofit organization that's located in the Finney Ridge neighborhood. It's 92 acres in total. The bear lot is one of their 5 parking lots in the zoo at 1.7 acres. It has 195 parking spaces and is connected to the City of Seattle combined sewer system and receives an annual rainfall of 38 inches.
In order to establish a baseline for our project, we found the overall basin delineation of our site. This was found through the usage of a LiDAR and a surface. In order to determine the overall subbasins, we analyzed the existing conveyance and determined the subbasins based on the catch basins. Given the overall basin and the subbasins, we found that the flow is as follows. We plugged the overall basin area and subbasin areas into the Western Washington hydrological model in hand with the land use type and found for our given site the current runoff condition are. For 2-year storm, it is 0.63 CFS. For 25-year storm, it is 1.09 CFS. And for 100-year storm, it is 1.32 CFS. These values are small, meaning that it reduces the zoo's abilities to significantly reduce CSO events. However, for smaller runoff values, they carry higher concentrations of contaminants and debris. Thus, the implementation of green stormwater infrastructure would aid in environmental benefits.
As shown in the picture above, there's the bear lot, and stormwater runoff from the bear lot enters Seattle's combined sewer system. Under typical conditions, the water flows to the West Point treatment plant for treatment and eventual discharge into the Puget Sound. However, when the system flows exceed capacity, water is rerouted and discharged without treatment into surrounding natural bodies of water. For the runoff from the bear lot, these reroutes happen at the points shown in blue and eventually discharge into the Ship Canal. While the runoff values from the zoo bear lot are small due to the smaller area of our site, the zoo is still conscious of the effects that they're having on these CSO events, have detrimental effects to the environment as well as public health.
For our design alternatives, we will have 3 different alternatives. Alternative 1 will be create no action, followed by alternative 2, which requires a environment tension with vertical walls and a permeable pavement. Alternative 3 will require a viral tension, but this time it will be with slope boards and a permeable pavement.
So this is a cross-section of a bioretention cell with vertical walls. The flow enters through a curb cut where there are then layers of composted material, bioretention soil, and aggregate subbase, which aid in helping infiltrate the water. Additionally, there is space left for ponding depth to allow the water more time to soak into the ground. Because we estimated the infiltration rate of our site to be 0.1 inches per hour in alignment with the hydrologic soil group we're assuming to have on site, Seattle Stormwater Manual recommends implementing an underdrain to aid in conveying that water. In hand with an overflow, these two components prevent backup into the lot. This is a cross-section of a bioretention cell with sloped sides, which contains all the same components, the main difference being the walls are sloped at 2.5 to 1 in line with the Seattle Stormwater Manual.
For our cross-section of permeable pavement, it is divided in 4 different sections. Currently, there is the provisioning course, and every course will help with the filtration and decontamination of the water. In the solar underdrain, we have the connection to the conveyance, which serves with the water traveling through the pipe, and then finally we have the storage reservoir, which serves with slowing down water going faster into the ground.
On our first site visit to Woodland Park Zoo, we noted the lush greenery that persists on the site. On the bare lot, there's 3 islands, with on average there being 6 conifer trees per island. This is an example of one of the trees on site. This is important as per the Seattle Department of Construction Inspections Manual. During construction activities, tree root zones must be protected. In the manual, it states the tree protection zone and tree root zone A. The tree protection zone is determined where 1 inch of tree trunk radius, 1 inch of tree trunk diameter equals 1 foot of tree protection zone radius. Thus, for the 66-inch conifer tree, it has a tree protection zone of 132 feet. For tree root zone A, that is 1/2 of tree protection zone. Thus, for the 66-inch conifer tree, it has a tree root zone A of 66 feet. These are all the tree protection zone and tree root zone A's of our site. The most notable that was site constraint is a tree root zone A. Another site constraint we noted is in the northernmost parking lot. This would not be a feasible location for GSI due to event staging and exhibit interchanging of the site. The permeable pavement would not be feasible.
We wanted to maximize the amount of GSI that we were able to implement, and the trees and the staging area were the main constraints we faced in determining the best size and locations for those. But we determined we were proposing 6 bioretention cells and 1 area of permeable pavement. Shown in red are the bioretention cells, and if they have vertical walls, this would provide 3,700 square feet of bioretention bottom area. If we slope the walls at the 2.5 to 1, shown in the black outlines, this provides about 2,000 square feet of bottom area. The permeable pavement, shown in purple, is about 4,500 square feet, and combined, these features do not exceed that 30% allowing disturbance within the tree protection zones and do not encroach into the tree root zone A's. In order to connect the underdrains and overflows previously mentioned to the existing system, we are proposing the new pipe shown in yellow. It's about 566 feet, in which the water will flow from the bioretention cells as well as the permeable pavement to tie into an existing catch basin that is on site. And the slopes of these pipes range from 0.5% to 3.2%, which allows for gravity flow.
Considering our site restraints and coming up with our proposed GSI layout, we were able to model a project in WWHM. This figure shows our current conditions for our basin, which is divided into 5 sub-basins at the top, connects to a downstream connection. This figure represents our GSI layout for both permeable pavement and bioretention. Sub-basin 2 connects into a flow splitter, which splits into permeable pavement and its corresponding bioretention area, while sub-basin 3 flows into its corresponding bioretention area and also connects to a downstream connection. From WWHM, we were able to obtain peak flows for a 2-year, 25-year, and 100-year flood, and for all 3 alternatives, as well as our pre-developed condition, which assumes completely forested land, and is why it is significantly lower than our alternatives. From WWHM, we obtained a 21% reduction for both alternatives 2 and 3 from our current conditions. This graph provides another representation of our WWHM data. The green line represents the pre-developed flow, while the blue line represents flow for alternatives 2 and 3, and the purple line represents the current conditions for alternatives 1.
Cost estimates for each alternative. Alternative 1 will require no cost. For alternative 2 and 3, this will require different cost estimates that we will have. For example, we have the progression and excavation. For alternative 2, it will be slightly more expensive than 3. For the temporary erosion and sediment control, all alternatives will require the same amount of money. For the drainage, alternative 2 will be more expensive than 3. We have surfacing also, both having the same cost, followed by landscaping, which in this case, alternative 3 will be more expensive. And finally, we have the signage, with both alternatives being the same cost, but overall, alternative 2 will be more expensive than 3.
In order to determine our chosen alternative, we took a qualitative approach. The following categories we looked at were flow control, community impacts, utility impacts, long-term impacts, maintenance, constructability, and construction costs. For alternative 1, which is no action, this serves as a basis for looking at other alternatives, but the most notable categories were flow control and community impacts. This would be because it's leaving the bear law as is, thus it provides no environmental benefit, and it provides us with no educational opportunity for the community. For alternative 2 and 3, the results are very similar, with the only different category being safety. This is because for alternative 2, due to the bear law being a high pedestrian area, the vertical sides of alternative 2 would pose potential hazard. Thus, our chosen alternative was alternative 3, sloped bioretention with permeable pavement, and next we'll talk about the additional ADA requirements.
In order to follow ADA requirements, there is currently 195 parking spots, with 4 being accessible. For ADA compliance, it needs to be at least accessible to 6 accessible spots. And then for changes to those compliances, that we need to add 2 accessible spots, followed by 1 in the access street, and raising the signage. Here's supposed to be a picture of where we will add the accessible spots. In this one, there will be a 60% redesign for the grading of the ground. But later on in the future, we need to regrade that section again to make sure that the slope is compliant for the parking lot.
Since our picture is not loading, I will add, we are proposing to change the striping on the 4 existing spots, and due to additional sloping of the lot adjacent to those spots, we are proposing the 2 additional spots be placed just north of the existing stalls, with one of the van accessible stall being located in one of the 2 stalls.
Thus, our final recommendations for part 2 is permeable pavement and handle slope bioretention and the additional ADA requirements. Thank you.
We have a slide that asks for questions, but it's also not loading, so if you have any questions, you can ask them.
I noticed the long-term maintenance was shown as moderate for this option. Is that related to the permeable pavement? I mean, that tends to break down with de-icer and also clogged. Is that something else considered?
Yes, thank you for the question. Just to re-articulate the question is for our given alternative, the long-term maintenance is we given an alternative, maintenance was given as moderate. We talked to not only the Hughes maintenance team, the board's cost team, the zoo does have previous experience with permeable pavement, and they will work with maintenance companies to make sure the permeable pavement is maintained. And due to their prior experience, they have high confidence in their ability to maintain that.
Yeah, so the question was, what's the weight capacity of the permeable pavement and can it withstand the load of cars? This is very dependent on the specific type that you have. So you can create permeable pavement out of different materials, pavers, etc. Those we did not specify, those would be determined later on. But in general, they are able to be used in parking lots, but more heavy than car loads over time will compact them, which makes them less effective, which is why we had mentioned that staging area where when they need like more heavy duty equipment, I don't know, maybe these forklifts, other heavy things heavier than cars that would compact it over time. So in the normal areas, parking, it will be fine.
Really great job, super neat project, interesting. Seems like we have a minute or two. I was curious, you probably learned a lot. What was the most interesting thing each of you learned on this one?
Being the first, I learned, I guess everything, AutoCAD, WWH, Seattle Stormwater Manual, but there's a lot of reading, a lot of trees.
Similar to that, I think the big overarching theme on that was giving yourself grace. I think you come in and when you have like all the trees on the side, you're learning what the tree root zones, and you're trying to figure those things out. And I think just letting yourself be able to know that it's okay not to know everything, and especially learning how to read the manuals. That's a big one.
I would say the manuals were the most fun.
I think the most interesting thing that I learned is that it's like really hard to do projects. I think in school it's like, oh, taking tests, doing homework assignments, that's hard. But then when in real life you have like actual problems like, oh, we can't even put anything there because there's a tree root there that we're not allowed to disturb under any circumstances. So learning how to adapt to the real life problems that we in those face.
I saw another hand at the back.
As part of either your modeling analysis or your evaluation, was climate resiliency elements, whether additional wetter, warmer, or drought resistance plants, were any of those considered as part of your analysis or evaluation?
I can take this one. Just to re-articulate the question, was climate resilience taken into account in our analyses and project development? Not directly, but we did talk to the horticulture team in other plants that they do have in the other areas of the zoo, and what would make it beneficial for them, and what plants would best thrive in these regions of the parking lot. We do not directly analyze this in relation to the scope of our project, but that would be a great avenue to look into.
I will add to that is part of the reason why the zoo came to us with this problem is they are aware that implementing green stormwater infrastructure and more green areas like this can help with climate resiliency and would provide that benefit, which is part of alignment with the sustainability, why they wanted to do this, and why even though we looked at no action as alternative, we knew that we were going to choose an option with implementation. Or we were pretty sure, I guess I should say.
Any other questions? Thank you.
Okay, and now immediately we invite them back.
All right, everybody. Thank you so much for being here today. Good afternoon. We are the Environmental Science Project Team 26.1. My name is Kat. This is Izzy, Liliana, and Amanda. And today we're going to be discussing our investigation of optimal drone flight parameters to capture water surface features. So this is just a quick outline of our presentation today. We're going to be talking about a little bit of background and key terms. We're going to be talking about our initial problem statement given to us by our sponsors. And then we're going to get into our experimental design and our accuracy metrics, and then our conclusions from the study. So this is our team structure. We were lucky enough to partner with Snohomish County Surface Water Management, otherwise known as SWIM. We worked under Dr. Gichao An. Katie Shank, who is with us here today, so thank you for coming, Katie, and Olivia Duane. From Seattle University, we had Dr. G serving as our design coordinator, and then we also had our faculty advisor as Dr. Lauer, and the four of us were project scientists. So some background about our sponsors. So SWIM is responsible for monitoring and measuring the ecological welfare of aquatic habitats throughout the county. Currently, one project they're working on is removing invasive fragrant water lilies throughout surfaces in the county and measuring how effective that treatment is. So one of the sites where they are treating these water lilies is at Lake Rossiger, which is a little bit outside of Everett. It is a 3-basin natural lake, and we are focusing on the center basin. And this is about 40 acres and a little less than 10 feet deep, so the shallowest of the 3 basins. And here they are currently testing new drone monitoring methods to increase efficiency of this treatment non-invasive.
So the steps to produce an orthomosaic using aerial imagery begins in the field using ground control points and surveying them. These are used later in processing in order to correct the geospatial accuracy of the final orthomosaic. Next, the actual aerial survey is conducted. This is done using a pre-planned flight path as well as a predetermined image overlap. These images are then imported and processed using a structure from motion technique. This uses highly visible common points within overlapping images in order to stitch them together. This resulting model is further processed and produced into a highly accurate large map called an orthomosaic.
As you can see on the right, SWIM's current orthomosaics are extremely pixelated and contain large gaps over the surfaces. And this is a problem for them as they can't conclusively determine lily pad presence or absence in those areas. Some of this is due to challenges that are inherent to mosaicing over water, such as a lack of distinct tide points in overlapping images, which prevents proper image alignment and stitching. Surface glare off of the water also results in visual artifacts, and wind poses additional challenges. As you can imagine, it's pretty hard to accurately capture a surface when that surface is actively moving. Our task is then to determine the optimal parameters, identify the most influential conditions, and develop high-quality, seamless orthomosaics or SWIM to accurately capture surface water features. We used the DJI Mavic 3 multispectral drone for all of our analysis. It is equipped with an RTK module, which is essentially like a really high accuracy GPS on the drone. We also used a kind of 2-phase experimental design in which preliminary test flights were conducted at Union Bay, Seattle, which has a similar depth and vegetation features as Lake Rossiger, but is a little bit closer to home to us. The results of these preliminary flights then informed more fine-tuned testing and analysis at Lake Rossiger. We used a pairwise design for all of our flights as there are many different environmental conditions that are changing all of the time, so it is difficult to directly compare two flights. So we only compared flights where one variable was altered.
So what were those variables that we were changing at Union Bay? First, we tested flying with 2 different altitudes, 200 feet and 400 feet. We also tested two different camera angles. A nadir one, where the camera is pointing directly down at the ground, or oblique, where it's pointing at a 45-degree angle. We tried the use of a polarizing filter, which was a small filter we applied directly to the drone's camera. The purpose of this was to mitigate sun glint off of the surface of the water, essentially acting like sunglasses for the drone. We tried 3 different flight paths, that being north and south, east and west, and then a grid combination of the 2 of them. In addition to all of the different drone parameters we changed, we also flew under different environmental conditions, this being sunny and overcast. And lastly, we processed our images in 3 different softwares: Metashape, Drone to Map, and Web ODM.
So once we finished all of our preliminary flights at Union Bay, we were able to narrow down what we wanted to test at Lake Rossiger. So from our tests at Union Bay, we confirmed that we wanted to fly at 400 feet as they were the most successful in the final orthomosaics. But we did change how we tested the flight path angle. So the sun changes position throughout the day, but it's not doing so in perfect cardinal directions. So to accommodate this and consider this, we flew either perpendicular or parallel to the sun's path. Another thing that we were able to settle on was the software. We selected Metashape because it had the highest percentage of image alignment compared to the other two softwares. And then lastly, we added a new parameter where we put these little buoys. We put about 3 of them out on the lake's surface. And this was to add additional visual features so we could hopefully have better image stitching and reduce those gaps. So now we have all these orthomosaics. How do we know that they're any good? Well, we came up with 5 different accuracy metrics to measure the quality of these orthomosaics. Our first one was aerial extent. So we constructed out of wooden planks and weighted rope, artificial lily pads, and we deployed them out in the middle of the lake. Once we stitched together our orthomosaics of the raw images, we were able to identify those lily pads in the orthomosaic. And using ArcGIS Pro, we went ahead and traced the outlines of these lily pads. And then because we also have a known area of these wooden planks, we then compared the two, came up with a percent error and a relative standard deviation.
Next, we found the percent images unaligned. This is a representation of the success of image stitching. This image depicts every known location of an image that was taken. A blue dot means an image that was unaligned and did not stitch together, therefore is exempt from the final orthomosaic, making gaps. Next is point cloud outliers. This is a representation of the visual noise within the orthomosaic. A point cloud is a 3D representation of individual points, each with their own spatial coordinates. And we then applied a cross-section across the water surface of the lake and the point cloud, and all points greater than 0.5 meter above the water surface were calculated as, or labeled as outliers. These outliers were then compared to the total number of points within the orthomosaic, and we received the percent outliers. Next, and finally, we did the lily pad percent error. This was done first by conducting a 50-foot aerial survey of our sample area. This acted as our ground truth, as it was a highly accurate depiction of the lily pad locations. We then did a binary presence assessment. This was done by applying a grid on our sample area, and within each cell of the grid, we assessed if yes, there was a lily pad present or no lily pad present. We then took the results from the 50-foot survey presence and then the results from our orthomosaic lily pad presence and compared them in order to get the percent error.
We then looked at the total range for all the values for each metric and divided it into 5 equal bins excluding outliers and scored all of our orthomosaics. We then assigned a weight to each of our metrics based on the priorities expressed by our sponsors and calculated a weighted score. These weighted scores were then standardized by dividing by the total number of possible points. And now, our final results. Here we have each parameter that we tested, the optimal condition, and the average difference in their standardized score. For example, we found the 400-foot altitude images to have a 9.25 increase in its standardized score over the 200-foot images. So our final drone parameter recommendations flying at a 400-foot altitude with a nadir camera angle, a flight path that is perpendicular to the path of the sun, and utilizing buoys as seated tide points. The results of our polarizing filter testing were inconclusive due to conflicting results in replicate trials. Our optimal environmental conditions were sunny weather and low wind. Our wind results are very consistent with literature existing already. However, our weather conditions really weren't. We believe this to be due to the shallow nature of both of our basins. In sunny weather and in shallow water, there is enough light to see all the way to the bottom of the basin. And that means that there are plenty of stationary and distinct tide points. Now let's put this into perspective just a little bit. First, we have this northern mosaic that we started out with using Snohomish County's images. There's gaps and pixelation. This is processed in the software that they currently use, Drone2Map. Now we have those same images, but processed into Metashape. It got rid of all of the gaps, but it also introduced large visual artifacts. And now, here we have, using our methods, orthomosaic processed in Metashape, showing highly accurate and increased clarity and quality.
So our results are looking pretty good, but we wanted to do one last validation. This involved taking 5 transects in the field and hand counting all of the lily pads within a specified distance of the transects. Then we flew flights at 50 feet, 100 feet, 200 feet, and 400 feet to see if we could count the same number of lily pads in those orthomosaics as our ground truth survey. Then we standardized our results to be on a per square meter basis, and we got these results. As you can see here, all 4 altitudes had roughly the same error, being about less than 1 lily pad per square meter. This indicates to us that flying at 400 feet is suitable for our task of capturing water surface features. But what if you don't have Metashape to do this analysis, which is the case of our sponsors? You can also use our methods to process images in Drone2Map and WebODM and get high quality seamless orthomosaics, proving that our results are applicable across multiple softwares. And with that, are there any questions?
Good question. Did you guys explore using different percent image overlaps? And what was, if you did, like what sort of conclusions did you make from that?
We generally used a standard percent overlap of 70 front overlap and an 80% side overlap. This is just saying how much the images are overlapping when the drone is flying its path. We did do a few flights at some different overlaps, but that was an accident. Thank you for the question.
So this was meant to capture surface water, so surface lily pads, but it looked like you could kind of see a lot of submerged aquatic vegetation on the edge of the lake. How good do you think it would be at finding vegetation maybe a couple inches or centimeters below the surface?
Yeah, so that's a really good question. To reiterate, the question is, how do we think our methods will fare to capture submerged vegetation? It was something that we actually explored. This is getting into like a little bit of a side project that we did, but due to the treatment of the lily pads, there's been uplift of sediment from the bottom of the lake. And in some of our orthomosaics, you can kind of see it. They're forming these kinds of islands. And you can see both what has already breached the surface and also a little bit of what is just underneath the surface. And they need to remove these islands. So, and to get a cost estimate for that, you need to estimate the area. So as an aside, Amanda and Izzy delineated the areas in our GIS Pro, and we're able to find pretty different values for what is on top of the water and also what is underneath the water. So that's just one application that's already been used. In general, the higher quality, the higher resolution, the better your orthomosaic is, the farther underneath the water that you'll be able to see. So in that instance, if you're trying to capture submerged vegetation, then the sunny conditions that's providing the light to do so is going to be even more important than if you're just capturing stuff on the top.
Semi-related, is a lily pad in January look the same as a lily pad in the summer versus other parts of the year?
I'm so glad you asked that question. One of the things that we actually came across when we were discussing this project with our sponsors, so to restate the question, does the presence of lily pads in January look different than they would now? The answer is yes. So while invasive, these lily pads are seasonal. So Another big reason why we wanted to add that aerial extent metric was so we could have features in the middle of the lake to look at, because when we were flying around April, the lily pads are just starting to come in and they tend to peak and bloom around this time, which we couldn't do those flights now. So we ended up having those artificial lily pads also serving that purpose, since they're only going to be in the edge.
One more question.
Yes.
Okay, all right. Great work, Wes, as always, but did you find anything else, and this may be more for Snohomish County, as you collected all this data and the lily pads, great stuff. Did you find any other things that surprised you, derelict boats, oil derelicts?
This monster.
Yeah.
Z boats.
We communicated with a lot of different community members over there, which was really great. And we got set up, like we were staying on someone's boat the entire time, which was really, or we called it the gazebo because it was a gazebo boat. But I think the most interesting thing was probably the sediment islands, because originally I thought that they were just sand beds and that we could walk on them, but you can't walk on them and you would fall through. And also, yeah, I think talking to the people, and yes, there was like derelict boats and there was like a derelict slide in the middle of the lake that I really wanted to slide down because that wasn't an option. But yeah, it was really, there was lots of fun stuff other than just the project out there.
Cool. All right. Thank you.
Next project was science, 360.
You guys are ready? Oh, yeah. No. What? Oh, I'm not. I've been in a lot, but not. I get problems.
Hello, everyone. We're team 2618, the Resilient Forestry team, here to present our capstone project for creating a cloud-hosted geospatial database. My name is Tynan Matthew.
My name is Olivia Zhao.
I'm Jason Stacy. My name is Tony Nguyen.
And our sponsor liaisons are Miles Lefebvre, Sean Geronimo, and Brian Fuentes, and our faculty advisors, Dr. Burkhard England. So our sponsor, Resilient Forestry, supports ecological forest management through science, planning, and geospatial analysis. So in simpler terms, they use data to make informed decisions about forests. And a lot of the work they do depends a lot on map-based information, such as satellite layers, vegetation data, soil data, and environmental layers. And these data sets help answer questions about forestry conditions, climate impacts, wildfire risk, and long-term planning. So because this work involves a lot of large amounts of spatial data, resilient forestry needs a reliable way to store, organize, and access spatial data. So our project supports this need by helping move their workflow from basic file storage to a more centralized cloud-based system. So our project focuses on building a cloud-hosted geospatial database. A geospatial database is a database that is designed for information that's connected to location, like coordinates, boundaries, and map layers. The goal is to give resilient forestry a more organized and scalable way to manage the data sets they use for forestry analysis. Over the past several months, our group has worked on designing the system architecture, setting up the cloud environments, and creating workflows for storing and accessing spatial data. So currently, many of resilient forestry's data sets are stored in Google Drive. While Google Drive is useful for sharing files, it has its limitations when it comes to managing large geospatial data sets. As the number of files grow, it becomes harder to maintain a consistent folder structure, track different versions, and keep important information about each data set organized. So it can also be difficult to manage permissions in a detailed way, such as controlling who can view, edit, and manage specific data sets. For a company working with large geospatial data sets, these issues can slow down analysis and make the data harder to maintain over time. So to address this, our team worked on a centralized geospatial database hosted in the cloud. The main technology we used is PostgreSQL with PostGIS. PostgreSQL stores the data while PostgreSQL stores the data while PostGIS allows the database to work with spatial information like points, lines, polygons, and map layers. This gives resilient forestry a more structured system for managing data sets, permissions, and metadata. And instead of relying only on folders and individual files, the data can be organized in a database that is easier to search, maintain, and expand.
So the first key task of our project that I'll be going over is converting all of Resilient Forestry's datasets into a cloud-optimized format. And so Resilient Forestry is working with two types of data, vector data and raster data. The image on the left is of a cloud-optimized geotiff, also known as a COG, which is the cloud-optimized version of a raster dataset. And you can see the image on the right is a geoparquet, which is the cloud-optimized version of a vector dataset. But before we converted the files, first we had to download them from Google Drive. And all the files in Google Drive were stored as a zip file. So first we had to write a script to unzip all the files, and then sort those unzipped data sets between vectored and raster data. Then we had one script convert the vector data sets into geoparquets using the GeoPandas Python library. A different script handled converting the raster data into COGs using the Geospatial Data Abstraction Library. After all of these data sets were converted, we were able to upload them to the company's Google Storage bucket, which is just an easier and more scalable way of storing large files compared to Google Drive. So in total, 20 data sets were added to Resilient Forestry's Google Storage bucket, and converting all of these data sets to a cloud-optimized format significantly reduced the file size. One example of a vector dataset was reduced to 35% of its original size, while an example of a raster dataset was reduced to 64% of its original size. Since Resilient Forestry already owns this Google Storage bucket, handing all these datasets off to the sponsor is super easy. There are many benefits of cloud optimization.
As mentioned previously, the reduced file size, and this is extremely helpful because it saves on the cost of storing all the data in the cloud, as well as makes the data faster to process. Rather than downloading the entire dataset, subsets can be processed due to the way the metadata is organized. And overall, this makes Resilient Forestry's workflow more scalable and with improved performance.
So for this slide, I'm going to talk about the stack item generation script. First of all, what is stack? What does it mean? What does it stand for? So stack stands for Special Temporal Asset Catalog, and the stack item is basically a metadata file that is going to be stored as a JSON. So instead of only having our file in cloud storage, we are also going to keep a small record of it as a JSON. And the way that our script works is that first we start with a GeoSpatial file, and the script is going to read it and extract the important metadata that we need for creating or generating our JSON file. And so the main goal is standardization. We want all our data sets to be in the same consistent formats. Inside like each stack item, we have different elements. In the stack item can have, for example, a name, it can have, for example, a boundary box, geometry, or an asset link, or maybe a date. So this is really important for us because it is going also to help us connect our stack workflow to the rest of the system.
And now for our first of the two demos. The first demo is the Stack API demo, which is used to help load datasets onto QGIS. First, you'll need to be connected to the Google Cloud SQL proxy and Docker like I'm doing here. Once that is established, you can create a new Stack connection. The Stack connection name can be whatever you want, and the link will need to be the local 8080 to align with the Docker connection. Once you do that and the connection is created, the connection will show up on the Stack folder on the left, as you can see here. Then you can open up the connections and then open up your new connection. It will show up the date and it will show the date sets that are present that Resilient Forestry uses. To find out more information, you can right-click a file and find out details. In there, you'll find important metadata, including boundary box, geometry, date time, etc. But the most important part is when you scroll down to assets, there is a URL with a portion called the Virtual System Interface for Google Cloud Storage, or V6 for short. You can copy that link and use that link to directly load vector or raster datasets onto QGIS. For example, for this part of the demo, I'm loading in a raster dataset of Washington State as named CanCoff 2025, and it works just as you would doing it locally, except using that link. Once I do that and the dataset is loaded, you can see that it's now loaded as a new layer on QGIS. I proceed to do the same thing for a vector file, which is an outline of Washington State. Same process as before, you just need to find the V6 link, copy it, and then add a vector layer, and then you can paste the link and it will show up on the QGIS. This is very important for Resilient Forestry because it allows them to use a single API to find important metadata and also to directly load these datasets. But what about if the datasets are really large or you just want to see a portion of it? Well, that's where our next demo comes in. Next slide. Our next demo is a clipping demo, which is another important task of the project. This is because datasets can be very large and loading entire datasets can be very cumbersome time-wise and resource-wise. Here I'm showing you the first part, which is the vector. So here's how it works. First, you need to paste in the V6 link you found in the previous part of the workflow, which is the Stack API. In this case, it is a GeoPark K of Washington State. And then you have a local area of interest on QGIS that you use as a digital cookie cutter. That is used to clip out the portion that you want to keep, and everything else is disregarded. Then you can save it to a local file on your PC. Here I'm naming it clip state for GeoPark K. This is for demo purposes. You can name it whatever you want or say whatever you want. And once you click run and the process runs, in just a few seconds, it will output a new layer, which is the clip portion of Washington State that overlaps with the area of interest only. The same process applies for raster datasets, and the process is almost exactly the same, but with one key change. With raster datasets, whenever something happens to a raster dataset or you change how it's viewed, it is resampled. So there's also an additional resampling method. I'm choosing near for this one. It's called nearest neighbor because it's the simplest. But there are other methods you can choose in the menu. Here I'm saving it as a GeoTIFF file. I'm doing click copy, and I click the run button. Well, compared to vector datasets, it will take a little bit longer than vector datasets to do the process because raster datasets are much larger than vector datasets, and because they are made of tiles that have to click each individual tile. I sped this up a little bit, but once it is finished, now you can drag the new file that's loaded on your PC directly as a layer on QGIS. And as you can see, now the new layer only shows the raster that overlaps with the area of interest. This is very important for resilient forestry because it allows them to quickly load the parts of data that they need and saves them time loading these big data sets and gives them more time to actually do the important analysis work that they need to do.
So for this slide, I'm going to talk about how we connected the stack workflow to the rest of the system. So we needed to achieve 3 important tasks. The first one, it was for each data set, we needed to add metadata and turn the metadata into stack items. Each item is the representation of the specific or individual data sets into the group. The second task, it was working or creating a workflow manual so our sponsor can easily use or reproduce the same process when the project will be ended off. The last one, it was modifying the metadata to include a V6 link, which is really important because it helps us to have access to the files that are in cloud storage directly instead of having to downloading them locally. So these 3 pieces are really important to us because they help us having like a more complete workflow and better organized and prepared for future users.
So now that we've handed off the project to Resilient Forestry, we envision that future capstone projects will continue to work on this project. And so some of the next steps for things that can be improved upon are, first, making the steps to connect to the database more beginner friendly. It would be easier if we had a background service run the Cloud SQL proxy instead of having the user start the Cloud SQL proxy. Next, we could add more server-side operations besides clipping. One example would be reproduction for raster datasets. And finally, adding tools to make expanding the database easier. This includes improving the integration of the stack workflow and also including operations within Python and R. It would be nice if it was easy for Resilient Forestry to add all of their datasets to this database instead of right now where it just has only the common datasets. And so that concludes our presentation. Thank you all so much for listening, and let us know if you have any questions.
When you have the input maps, are they all fairly consistent in their kind of the form, or is there some kind of issues that you have to deal with in dealing with? Because a lot of times you're dealing with data that's large databases, there's inconsistencies or things are in kind of different formats or different levels of resolution, things like that. Do you have to deal with any problems like that?
I can answer. So luckily for us, the clipping script automatically deals with the situation if the error, because each dataset has a projection number. And if there's a difference between the area of interest projection number versus the original dataset number, the area of interest projection will be pre-projected to match the original area of interest before the clipping is done. This is so that there is consistency and there aren't any errors with or any mismatches with the clipping operation. Yes?
For that compression ratio that you achieved, were there other tests that you did that you got maybe different compression ratios where you started to achieve diminishing returns? I can't remember, it was like 40%, I can't remember what it actually was. Were there other ways that was evaluated?
No, there wasn't other ways. I just picked certain examples of data sets that I noticed that their size decreased significantly.
I have a question. So, surprised the previous team didn't ask because they had lots of problems with the raw images. Before you process a data set, you can end up with many individual small raw text images. Do you have any thoughts about, and managing those online was a real pain. Do you have any thoughts about how you can incorporate management of raw imagery in a system like this?
That's an interesting question. I think to answer that, back when you saw the demo, there was actually multiple different area of interest parts to show that it's pretty resilient with multiple shapes. So I think the same kind of would apply here. If there were multiple geotiffs, it would take any part of that geotiff that would overlap the area of interest even and discard the rest of it. So it can handle both different geotiffs, different shapes and also different, segmentations, as long as it overlaps that area of interest.
Yeah, thank you.
Hi everyone, we're team 2606, and last year we've been working on EcoHarvest. I'll quickly introduce our team. I'm Gurpreet. Alongside me is Daniel, Ethan, and Ryan. We had the pleasure of working with Angela Fletcher, who is a senior researcher at Earth Economics, and Professor Zach King as our faculty advisor. A little bit of background on our sponsor, Earth Economics. Who is Earth Economics? Earth Economics is a nonprofit organization located in Tacoma, Washington, founded in 2004. Their vision is to quantify the benefits of nature for decision making. For the past 20 years, they had a research database over 10,000 records, which is following their vision, a future where people and the natural world are central to all economic decision making, which leads us to our problem and solution. So currently, the problem at Earth Economics is the researchers are taking a lot of time manually reviewing these research articles, which can be slow, repetitive, and inconsistent. Sometimes there's irrelevant articles, which take a lot of time. So our solution is EcoHarvest, which is a desktop application that uses AI to screen articles against relevance criteria that was provided by Earth Economics. In this past year, what we built is a standalone desktop application which accepts article input through uploaded PDFs, or users can search articles through the journal name, AI scoring against 8 criteria from Earth Economics, a results dashboard, which allows the user to get an in-depth review of how the AI scored the article based on accept, reject, and review. A database storage, which allows the team to revisit, come back where they left off, and also export as a CSV. And we added a configuration page, which allows the user to also switch between different OpenAI models and also edit the prompt according to if they want to add more criteria in the future. And I'll be handing it off to Daniel.
Okay, so I'm gonna go over some of our pipeline. We use the pipe filter architecture, it's called. But before we get into that, does everybody know what an API is? Can I get a show of hands? I know I have my fellow researchers here. I know my brother does, but Mom, I'm sorry, I'm not trying to throw you under the bus, but I don't think you know what an API is, but I'll tell you, it's okay. An API is an application programming interface. So I'll give you an example too. I'm a let's say I want something from a service, I want to get something from a company. Well, code is very structured. It has to be structured. I have to have a set of parameters. I have to tell it what do I want. So you could give an example. Pretend I'm a waiter, or pretend I'm not the waiter. The company's the waiter. I'm ordering at a restaurant. I have to tell the waiter what I want, basically. So the word API is going to come up a lot. So I don't want you guys to get freaked out. Yeah. So when we start off, we get our PDFs from Elsevier, which is we use their API. We fetch these PDFs. And after we fetch the PDFs, we adjust them into our tool, and we take some metadata. So what is metadata? Well, it's just some associated information with the PDF. So, things like the author or the DOI, which is the identification number of the paper or when it was published. After that, we send it to OpenAI, this is a tongue twister, OpenAI's API. And that's when we get our relevancy score. And it's called inference. And after we do that, we put it in our database. We have we use a cloud-hosted database called MongoDB. And after that, we can actually use that to go back to I didn't explain this. This is a user interface. UI stands for user interface. So that's what our client interacts with. And so then we can upload it back to our UI and they can see all the results. This looks daunting. This looks scary. You don't need to pay attention to all of it. I'm just going to go over some few quick. This is more for people who are interested in what type of libraries we use there, stuff like that. But so I talked about how we ingest articles through the API, but we also have a PDF upload function. And this is actually how we tested our product because we had an existing database that was provided by a sponsor. That was basically okay. We have these ones we know were rejected. We have these ones we know were accepted. So we can test basically to see how well the AI model actually works. And so that's why it is also helpful. And then we only have access to 3 journals. And so maybe if they wanted to, a fellow researcher from another company sent them a cool paper and they wanted to upload it, they can. So yeah, and then after that, we feed it to our grader, like I said, and it goes into the MongoDB database. And I'll touch on this too, CSV export. I'm sure you guys have used Excel. You guys know what Excel is, right? Well, so they have an existing database of 20 years almost, actually. And so it's a big database, but it's Excel's format. So they wanted to be able to add on to their existing database what our tool would actually give them. And so that was an important feature. And yeah.
Sounds good. So now that we know a little bit about our data processing pipeline, as well as the components that make it up, I want to talk a bit about the steps we took as developers to turn this solution into code. So for collaboration, we utilize GitHub following a branching strategy. We went with branching just to keep a consistent main branch so we could provide regular demos to our sponsor. For project management, we followed Agile Scrum On. We had weekly meetings with our sponsor as well as our faculty advisor just to maintain alignment with what they wanted. We followed Scrum ceremonies regularly within the dev team, and we maintained a Kanban board to track our development. Finally, testing was a central component to our development. We maintained 80% test coverage over the course of the project, utilizing unit and integration tests. So now I'll just give you guys a roadmap of what we worked on throughout the year. In fall quarter, we really focused on setting ourselves up for success. We developed various technical white papers, things like architectural and scope documents, and we developed an initial prototype. And after getting approval from our sponsor, we went ahead and fleshed that out in winter quarter. Winter quarter is where we developed our MVP. We integrated or implemented our initial data processing pipeline from ingestion to scoring to persistence. Then we developed a intuitive GUI so we could start giving live video demos to our sponsor. And we developed some performance metrics to ensure that our AI scoring approach was effective. Finally, in spring quarter, we really focused on aligning our tool with our sponsor's needs here. We implemented various features from OCR-based PDF text extraction. OCR stands for optical character recognition. This is just to pull data from roster-based PDFs. And then we also implemented our configuration menu that we talked about earlier. We're looking forward to packaging and handing off our tool to Earth Economics next week. Yeah. Moving on. So I just want to circle back to those accuracy metrics because this is really the heart of our tool. And we were able to run some tests over a 50-article test data set. This test data set was manually labeled by a research set Earth Economics, providing us a sort of ground truth to compare against. We ran the same test articles through our data processing pipeline and found that we were getting above 80% accuracy in scoring. This is well within the threshold that our sponsor required.
So we continue to go with LLMs and prompt engineering. Along with this, we took a note of scoring consistency. This was an important metric for us to measure just because large language models are non-deterministic in nature, and we're able to achieve high consistency through changing the model temperature to 0 and aligning the prompt properly. Alrighty, and just to conclude, I want to reiterate that we're able to build a standalone desktop app that works end-to-end, from ingestion to scoring to persistence. We were able to prove that prompt engineering with large language models is an effective way to streamline manual data classification workflows. And what this means for Earth Economics is that their team will be able to spend more time making insights on data and less time trying to source it. I'm gonna hand it off now to Ryan for a demo.
All right, Ryan. Hello. Okay, so my name is Ryan, and I will be showing the demo. Yes. Okay, so basically this is our GUI and it has 3 main features where we can upload and analyze the PDFs. We can also search for specific articles using the journal APIs. And finally, we can also go back and look at the results and history of previously graded articles. So if we go over to upload PDF, over here is where we can upload a PDF article and then have that graded. So let's just say we choose an article that is known to be good, then our expected score is that it is an accepted article for our sponsored use. So we can see that's extracting the metadata and the text from the article. And for articles that are scanned, it'll use OCR. So right here, we do have a quick grade just to give it a faster result, and then it'll do a longer detailed screening, which is more important. So we can see that the article was accepted, and that's a good thing because it was considered a good article. And if we hop over to results in history, we can see that we can check out the session that we have. So we can see that the source was a PDF upload, the article was accepted, and we can see that it has all the title, the DOI, the year, the source, and that's just all the metadata that's extracted from that file. And there's a little summary as well. And here's the important part. So how our model evaluates the main criteria from these PDFs. So if we can see that primary study is an important criteria. So it will press details, and then we can see that there are citations that show and prove that those citations are in the PDF. That means it's not hallucinating, and we can have proof that it is a good article. And we can do that for methodology and study H as well. And hopping over to the search, this is where we can search the journal APIs. So there are 3 main journals. There's Ecological Economics, Ecosystem Services, and One Ecosystem. If we use the first one, and we will go towards the Browse Articles button, and we click it, it begins to fetch articles from the API with those filters from year 2020 to 2024. And we can see that articles are filling into the stream, and it'll give us a little preview with all the metadata pulled up. And you can see some of these articles that have a red background. That just means those articles have been processed already and stored in the database, so we don't really need to regrade them and remove tokens. So if I press stop, I will select 2 articles to be graded this time. Then we can press the grade selected button, and we'll have that running. This part should be sped up, so it shouldn't take too long. So right here, those articles are found to be 2 rejected articles, so not very good. And if we hop over to our stored articles tab, this is where we can show that all the previous articles that have been graded using the tool. And we can look here, you can see again all the data on why it was rejected instead of accepted. There's failing criteria. With that, there's citations to show that it passed and that it failed as well. going through land cover service disaggregation, standardization, methodology, and study age. Finally, we'll check the other article that was graded, and this one seems to have failed more criteria than the first one. And we can see that all those details again for the researcher to use.
Yeah, we were provided this by Earth Economics. This is not our domain. Our job was just building the
this is the config tab. We can swap out AI models, and there's an option to change the batch upload limit. By default, it's 10, so we don't accidentally upload 100 articles and use a bunch of tokens. We can also allow the user to customize their CSV that's exported. We can choose what columns to be included in the spreadsheet. And finally, we can change the AI prompt for the user if they want a different prompt as well. And that is our demo. So finally, I'll have some gratitudes. Thank you to Earth Economics and Angela Fletcher, who's our sponsor liaison back there. Thank you to Zach Yang, who is our faculty advisor in the back. Thank you to the Project Center. And thank you to my teammates, Gurpreet, Daniel, and Ethan for being awesome teammates throughout this year. Thank you.
Any questions?
Right here. Yeah, so first of all, very fantastic presentations, really enjoyed great products. So I have this question. So I know these research papers or like these studies, sometimes they can run really large and in pages, very long. And you mentioned you use AI for the scoring systems. So I wonder, with such like long and heavy data like that, what are the architectural designs or solutions that you use to handle like those studies?
Yeah, so this is a great question. So one of these things is in these journals, there's actually, and Angela notified us to us, but there's actually some where they're an aggregation of like tons of different research papers, and they can be 100 pages long, which means they're also going to have like, it's mostly citations too, and we don't even need citations. So actually, some of what we do is we actually parse it so that we just don't use the citations, and we actually try to stray away. Like ideally, we'd stray away from those larger collections because we prefer just like a primary study, which is just straight to the point. And 100 pages is going to be like probably like 100,000 tokens. It's a lot of tokens. So yeah, right here.
What were the design decisions that went into choosing to make it a desktop app instead of a server client-based architecture?
That is also a great question. Well, so our sponsor, they didn't want to run any code. So we wanted to make it all inclusive, really easy. That was actually probably one of the largest challenges actually, was incorporating all the libraries and everything we needed already in the package to send to our sponsor. And so that was hard, but we did it, and it was because they wanted it. So, yeah. Jacob.
First of all, great job, fantastic job, great presentation. My question is, how do your metrics fluctuate when you go from the default model to, for example, the nano model?
So all of our metrics were taken on GPT 5.2. That was kind of our baseline, or not baseline, but our default model. This was just because GPT 5.2 came out at the beginning of our project, and that's when we ran our metrics. We added the GPT-4 family of models just to future-proof our app. So we didn't run any metrics using them, but we just wanted to make our app extensible pretty much and future-proof.
Tony?
Yeah, great presentation, by the way. Thank you so much. I learned a lot from this. Question, how long does it usually take for article, and do you have any considerations on balancing accuracy versus speed?
Take this one. I can do it. So, wait, sorry, could you repeat your question for me real quick?
Okay, basically, were there any considerations like how long it run took, and also were there any considerations of speed versus accuracy?
So we pretty much handed off that logic to OpenAI. Pretty much however long our prompt and the full text takes to run, that's how long it takes to run. But these runtimes are very, very quick. It obviously depends on how many tokens are in the article, so it can vary if we have like a 10,000 token versus a 50,000 token article. But it's usually within maybe 10 to 20 seconds per article.
I'll tell you, it's much quicker than someone doing it manually.
There's one question in the back, and then we'll probably move on.
I'm fascinated. It's a great presentation, and this is just a discovery question for you also. I've been using a lot with Notebook LM, and I was wondering, is this married with something like that, or is it that you guys are using OpenAI to kind of collect the data and then creating your own ecosystem to review it versus with Notebook LM? I don't know if you're familiar, but you just upload source documents and they.
Yeah, so that's a great question, and Notebook LM is great, and we actually chose to use OpenAI because it was already part of their organization. And the thing we're kind of manually, yeah, you can upload PDFs and stuff, but you know, if you're searching through a whole journal of, you know, journals usually release in a year, at least this one, around 600 articles every year. So you know, if I don't want to manually upload 600, you know, art, but you know, that's what we're kind of trying to automate, and we do have a PDF upload function in our tool because, you know, they might have articles that come not from the ones we have access to. But great question. And yeah, I know there might be some Anthropic or Claude fans in here, or maybe some Gemini fans, but we just use OpenAI, unfortunately.
Thank you. Thanks everyone for being here for the session. There are posters and the reception outside, so please stay and
Good job, man.